ready to respond to an ever-changing landscape. We made that vision a reality, delivering small satellite constellations for high-stakes critical missions, embracing lessons of the past to craft the solutions of the future. We must meet the evolving needs of a rapidly changing world, reminding us that we must see beyond the ordinary to create the extraordinary.
All right, thank you to Millennium for being our presenting sponsor. Their support is really valuable. And with that, I'd like to introduce our second keynote speaker. Our keynote speaker is going to be Randy Yount from Millennium. Randy is a director of mission operations and engineering at Millennium Space Systems, a Boeing company. Millennium Space Systems is a small satellite prime delivering operational high-performance constellation solutions for national security space. Founded in 2001, the company's active production lines and 80% vertical integration enable the rapid delivery of small satellites across missions and orbits, LEO, MEO, and GEO. As director, Yount is responsible for overseeing the in-space and ground segment components of the company's satellite systems. He has more than 19 years of experience flying high-profile missions across orbits and vehicle types, with an emphasis on anomaly resolution and flexibility of operations. Prior to Millennium Space Systems, Yount was with the Boeing Company, focusing on GNC and spacecraft dynamics, operating more than 30 commercial and government satellites, and leading the anomaly response teams for in-flight vehicles across the Boeing 702 satellite fleet. Incidentally, he also happens to have earned both his bachelor's and master's here in aerospace engineering from Cal Poly. So, Cal Poly alum, please welcome Randy Yount.
Morning, everyone. All right. Really happy to see everyone here today. As was mentioned, I'm Randy Yount, so I'm the Director of Mission Operations Engineering at Millennium Space Systems. Really excited to be here. Really happy to welcome everyone to day 2 of the CubeSat Developers Workshop here. I'm excited to be here not just because I went to school here many, many years ago. It's a great school, it's a great program. This CubeSat, smallsat, where we're all at in this industry right now is where all of the growth is. For those who don't know about Millennium, the video told you everything you need to know, obviously. We were created about 20 years ago because we foresaw the need for these smallsat, CubeSat type missions and satellites in the industry. We've been pushing them for the high stakes, critical sort of national security missions ever since, and we have really met with a lot of success in that, right? But it's that forward-leaning, forward-thinking, the planning ahead to what the needs are going to be that has led us to the success we've had, and that's kind of what I want to talk about a little bit today. How you get ahead, how you stay ahead in this industry. It is a rapidly changing industry. It is not the same industry I joined when I first got out of school. It's not going to be the same industry a year from now, right? So it is constantly changing. And one of the things that need to focus on, so 3 key areas here, agility, flexibility. You need to be able to lean forward with your products, with your planning, and you need to learn the lessons from what you're doing. And those are not revolutionary things. Those shouldn't come as a surprise to anyone, but those are all really key to being successful in this industry. One of the things we hear from childhood is don't run with scissors, right? Don't take those risks, calm down, you're gonna hurt yourself. Sometimes you want to take a risk. Sometimes you don't want to just run, you want to sprint. And really what the industry is asking us to do right now is sprint. So you need to figure out how not to be reckless, but how to take those calculated risks, how to sprint without doing things that are actually gonna hurt yourself in the industry, but push forward as quickly as you can. One of the numbers that is amazing to me, both in its accuracy and its size. So there's firm Frost & Sullivan estimated there would be about 20,245 satellites launched between 2019 and 2033. It's a really precise number for them to estimate, which is awesome, but it's just a huge number of satellites, right? 10 years ago, that number of satellites would have been incomprehensible, but because of the speed at which we move now, the CubeSat constellations, the smallsat constellations, nobody is blinking an eye at those numbers in the thousands, and it's probably going to go up even more as these things continue to proliferate. So, you know, these small sats, the CubeSats, the rapid development has completely changed the industry, completely disrupted everything. One of the best examples of that is our Victus Nox mission. So I'm going to talk a little bit about that, sort of how Millennium executed on that and where those three things come into it. But before we do that, I got a quick sizzle reel, kind of show you a little bit of overview of the mission. So we'll go ahead and play that now. Awesome. It's always great to see the satellites going off into space. I never get tired of it. So what was Victus Nox? It was truly a sort of trailblazing effort full of those calculated risks that I want to talk about, right? So our customer basically came to us and said, we want you to do something faster than has ever been done before. 8 months to build, test, deliver a satellite. 60 hours to get the satellite from factory onto a rocket ready to launch. And then at a moment's notice, we could be at home, 3 a.m., having a beer, they'd call us up and say, in 24 hours, you are launching, right? And that's us and Firefly both. Nobody knew when we were launching. Nobody knew anything about it. So that is a crazy timeline. We were able to achieve it. How were we able to achieve it? So it's those three things, the agility and the flexibility, right? The company was built with that as part of our core culture, part of our sort of DNA, if you will. From the very beginning, we're able to pivot, we're able to adjust on the fly. So this program came in and was pretty disruptive, right? It's an important mission, we want to do it, but we have a lot of other programs. We have a lot of other things in the factory being produced. Our ability to adapt to that and be flexible, fit it in, and not really delay any of our other programs, that's huge, right? So the company's ability to just engulf this new program, be adaptive, be flexible, and get everything going was huge to this. And we've been doing that since our founding, 20 plus years ago. The whole thing, normally it takes months to do a lot of these things. We did them in days on the whole. So we pulled our satellite from one of our production lines. So we have an ongoing production line for a bunch of different satellites that we're building for other customers. We pulled one of those off, and that's 65% of the way there. But the agility and the flexibility to do that is one part of it. The leaning forward is the other. So our satellites are built mostly out of common components, common interfaces. They're interoperable, and they're very modular. So we could take a satellite that was built for one purpose, for one mission, for one orbit regime, and with very little alteration to the hardware or the software, create a whole new mission profile for a whole different orbit than it was ever intended for. And a lot of that is sort of leaning forward and understanding what the market is going to need. So our satellites, the hardware is a huge performance envelope. It kind of encompasses most mission types. Where we tune it is in the software, right? So the software is more important than ever for these kinds of missions. You've heard of software-defined radios, right? The satellites are getting more and more defined by their software rather than their hardware. And so with our modular components, we can easily trade out a couple of components to get ready for a new radiation environment, a new orbital regime, and our software is already built. It has all the features it needs for the functionality that this mission wanted versus the one it was doing before. So I think you saw in the earlier intro video, we're about 80% vertically integrated. That means we have our own star trackers, we have our own flight computers, our own avionics stack. But one of the other key things there is we don't just rely on our own in-house products. We can incorporate third-party as well. And one of the biggest struggles everyone in this industry is dealing with right now is supply chain, right? Getting the components in you need. So if we don't have a star tracker off our assembly line ready to go, we can go to an outside company, buy it, and integrate it with very little fuss because we have all that stuff ready to go, all the interfaces ready to go. And that helps so much with supply chain. That allows us to be really flexible and be agile with our products. And that commonality is what enabled us to get this program from ATP all the way to delivery in 8 months, right? We took a common bus, we did some minor adaptions, we didn't even really need to tweak the software, and we're good to go. And one of the things that has helped us there, and one of the things for everyone out here who is at it, especially the startup stage, early startup stage, starting their own business, the process and the long-term planning are where you'll be successful. And the fun of a startup, right, is that you break all the rules. You start with a clean sheet of paper, and you just do whatever you want, and it's going to be the best thing ever. But process is still necessary, and that's a thing that is a lot of startups don't like to hear because they think process slows you down, right? And it can, but it doesn't have to. Where you need with that process and that long-term planning is once you have a product and there's a market out there for it, people want to buy it, they're going to want to keep buying it. If you don't have a process in place, you don't have those long-term plans, you're not going to be able to scale. If you can't scale to meet that need, guess what? Someone else is going to come in, and you're going to lose that first mover advantage, and they're going to scale up, and they're going to produce what you were supposed to be producing, and they're going to take all of your business, right? So from the start, building in that process, that long-term planning is key to having a successful company. And then the final point, and that's sort of where Millennium learned those lessons, right, is learning those lessons in the fly. This is really where it hits home for me, especially being a Cal Poly alum, right? Because when I was here, and hopefully they're still saying it and drilling it into all the students, learn by doing, over and over and over. That's what Cal Poly is about. That's what this Victus Nox mission was, right? We were doing something completely new, learning all kinds of lessons along the way. And it's simple stuff, really. The logistics was the hardest part. You know, everyone's heard unknown unknowns. It's a horrible phrase, but it's still a good one to use. Things like electrical storms happening during fueling. Things you can't really slow down or stop. You're on too tight of a timeline. So how do you adjust for that? How do you still handle personnel safety? Cannot have people out there with hydrazine filling up tanks when there's lightning around, but you still have to move forward, right? So you have to pull things in parallel. You have to figure out what other work you can get done. You can't just relax and say, well, we got a 4-hour break, we'll pick it up later. There is no breaks, and the industry is going to keep getting faster and faster. Even on orbit, right, where most of my experience is, commissioning a satellite, we normally have a bunch of procedures we go through, check out the systems one at a time. As we're going through this, realizing that's taking a long time on orbit, as it normally does, start to combine data points from earlier stuff in new ways to realize we don't need to do all these checkouts, we can eliminate that. 5 minutes, sure, it saves you 5 minutes, but in a 10-minute pass, you have 90 minutes before your next one. 5 minutes can mean all the difference in the world between hitting your targets and completely missing them. So every little bit helps. The biggest lessons learned, though, were really in those logistics, right? Like the fueling, you can't practice that very well. We had one instance where a tube of thread locker had somehow been pierced, punctured, it dried out. We didn't have a spare. That was too much time wasted, right? Did it waste days? No. A couple hours to get a new one, but that's hours we can't afford, right? So even those tiny little things in logistics, when you're trying to go this fast, that's really where you got to pay attention. Even, I'll say, meetings, right? One of the things we noticed is coordination with subcontractors, coordination with customers. If you have that meeting too late in the day, decision doesn't get made till the next day, you waste the second shift, you waste overnight, you waste everything. So you have to really pay attention to every single little thing when you're trying to go this fast. And those are the lessons learned, right? You have to not just take note of them and then on your next program say, okay, here's what went wrong in the last one, here's what we're going to do better this time. You have to adjust in the execution of your program. You have to be willing to throw out your whole plans and readjust, start over again, and incorporate those lessons as you're going. That ability to adapt to uncertainty, right? To learn while doing and adjust on the fly, that is what made Victus Nox a success. So we took the vehicle from ATP to ready to deliver in 8 months. Against the 60-hour time to get it ready and integrated fueled on top of the rocket was 58 hours, even with the 4-hour electrical storm. We had 48 hours to then commission the vehicle and have it mission ready, able to do what the customer wanted to do on orbit. We did that in 37. So we not only completed the goals, we got ahead of them. Awesome. The next one's gonna have to be faster. The one after that's gonna be even faster, right? This industry right now is accelerating really quickly. The customers need capability now. They don't need it 10 years from now, and they don't want to have a satellite up there that is 10-year-old technology that was designed 20 years before it was even launched. They need capabilities, they need to iterate, they need to be able to respond quickly. And that's the whole point of Victus Nox, being able to respond on a tactical timeline rather than a long-term planning. So just kind of want to keep in mind those things, right? The things that made this program successful, the things that are making Millennium successful, that agility, the flexibility, the leaning forward, kind of looking at the future trends, understanding what there is, and learning those lessons, and especially learning them and incorporating them while you're doing it. So, you know, there's a lot of opportunities out there. This industry is exploding. I think these conferences are evidence of that, right? There's more and more opportunity for startups, for companies to make a difference here. So go out there, build your products, and get them to market, because we all need them. National security space needs them, commercial space needs them. We need them fast. Thank you. I think I'm good to take a couple questions. Anybody has any? Yeah, everybody's favorite topic, paperwork. We were lucky on that because our customer was able to push and get a lot of things done, right? When you're working with certain government customers, it makes some things easier. That's one of them. But the other part is still, it comes down to logistics, is understanding, we've been through this before, we know where the pitfalls are, we know where those blockages are, starting to work those as far ahead of time as possible. It's not to the same level as, say, our hardware and our software, but having been through that process before and knowing how to do it, it's the same thing, right? Don't wait to start talking to the regulatory agencies. The FCC is slow, right? Government agencies are slow. They are. So start early with all of that. Cool.
Any other questions? Okay, let's thank our speaker again. Thank you very much, Randy.
Thank you.
All right, we now have a break scheduled, and we'll begin the next round of presentations at 10 a.m. So see you back then.
from break, everybody. Next, I would like to welcome Shane Woods, Michaela Power, and Damian Fowler from 3U Cubed.
Good morning, everyone. Thank you for the introduction. We'd like to thank CDW for inviting us here to present. My name's Shane Woods.
Damian Fowler.
I'm Michaela Power.
We're senior computer science students at the University of New Hampshire, and we're part of the IMAP student collaboration. We're going to tell you a little bit about our CubeSat today and how we implemented command and data handling and our flight software routine. So the mission statement for the IMAP student collaboration is to augment the IMAP science return and to develop hands-on research experience for students and diversify the space science program. While we're formally called the IMAP student collaboration, we came up with the name 3U Cubed for our project. So that stands for 3 universities, 3U CubeSats, upwelling, uplifting undergraduates. The 3 universities we collaborate with are the University of New Hampshire, Sonoma State University, and Howard University. Each university will build an engineering model of the CubeSat, and then together we'll deliver a flight model to CSLI for launch in 2025. A little more about the mission. We have 2 student-built instruments on board, and we focus our work primarily at the different universities based on the experience levels we have. So at the University of New Hampshire, we work primarily on the instruments. Sonoma State works mostly on the ground station and the flight software, and Howard works mostly on the thermal. But with all that being said, we definitely collaborate a lot and help each other out.
Okay, now I'd like to provide you a brief overview of the subsystems involved in this mission, how they communicate with our onboard computer, and just some of the subsystems that the 3 of us specialized in. So to start, we have our electrical power system. This is a Clyde space-based electrical power system. It communicates via I2C, or integrated circuit communication. We also have a comms, a cube ADCS, and an instrument which is inclusive of an ERPA and UV PMT, which we'll go into farther, specifically Shane in the next slide. And all 3 of these communicate via UART. In terms of who specialized on what, I worked on the electrical power system, Damian worked on the OBC, and Shane worked on the instrument.
So the instrument design, we'll go into it a little bit here. The 2 student-built instruments are an ultraviolet photomultiplier tube and an electron retarding potential analyzer. We communicate with these through a STM32 Cortex M7 microcontroller. The way we communicate is that each instrument has an analog to digital converter, and we utilize the microcontroller's built-in serial peripheral interface protocol to talk to them. When we get the information back from the instruments, we'll packetize this data based on how it's coming back and then send it to our onboard computer, which will send it to our radio. A little more about how we structure our data coming back from the instruments. Each of our data packets, we have 4 of them, are structured very similarly. So there's a header byte. Each segment is 16-bit words. So the header byte, which we call a sync, is just a fixed 2-byte hexadecimal. That lets our onboard computer know when it's receiving data, which data it's receiving. So then we have a sequence 2-byte number, which tells us which packet number is coming back since the start of our data collecting. And then the remaining words in the packet are the actual data. So for our ERPA packet, it's just a 16-bit analog reading from the ADC. Same with the PMT packet. And then we also have a housekeeping packet for the ERPA that tells us the sweep voltage for the ERPA. And then just a general housekeeping packet that We send less frequently because it's a bit larger. That has readings about MCU health, temperature monitors on the signal board, and voltage monitors on the microcontroller. In our FlatSat design, we send this data back to a computer running a graphical user interface, so we can instantaneously get like human readable data and make sure we know it's coming back. In flight, we'll actually be sending it back to the OBC. So a little more about this graphical user interface. It was built by two of our fellow undergraduates, Jared Morrison and Jared King, who unfortunately couldn't be here. It's written in C++, and it's actually been like really helpful for our project. It allows us to get the data back from the instruments right away when we're testing, and we can see if anything's going wrong. You can kind of see that here. We have ERPA packet, PMT packet, HK packet, and they all come back in live time. And then on the left here, we kind of have different buttons and pins that you can turn on and enable voltage rails on the instrument. So yeah.
My portion of interest is the OBC. Specifically in this slide, it is about how the OBC receives the instrument data that Shane was just talking about, and how it eventually stores it onto the SD card. I have notes which I will go over while I go step by step through the diagram there. Initially, the OBC receives the instrument data via UART. Initially, we wanted to, our initial tests were to have the interrupt directly write to the SD card, which is a bad practice, and it didn't work. So we eventually had to come up with a better solution, which we ended up doing tasks with free RTOS, which is what the system uses. And we started with only one task, and our first test was to write to the SD card with that one task. That worked successfully, but then we needed to send the instrument data to the task, and that's when we got into another hurdle, and our solution with that was to start looking into inter-thread communication. What we ended up finding was two different systems that I think worked the best for this, which was message queues, which were provided to us by free RTOS, and the EnduroSat data cache. Each one has their own limitations and advantages. I ended up using both. Maybe eventually we will simplify down to one or the other depending on the results. After the initial task, we ended up making another task, kind of because of I/O specifically traditionally being slow. So I think it would be best if it was separated, and just in terms of making the code modular so that we could swap things in and out. Already, due to changing requirements, it has been considerably easier considering just the code is more modular than it, I don't want to say needs to be, but it's good that it's modular. And at the end, I just wanted to point out that the line at the end of the graph for the radio from the SD card, there's a lot more to it in between the SD card and the radio. There has to be a whole driver made for that, and that would be a whole nother block. So the other section I will be talking about is ConOps. The graph there is a relatively simple diagram of the different stages of ConOps depending on the status of the satellite. And I will be going into a few of the stages and explaining them, or I should say summarizing them, because there's a lot more to it than this. This is just a basic list. So first, we have safe mode. Safe mode is what the satellite initially goes into every time it reboots. So that could be due to an error or because it's just starting up for the first time. It will remain that way for a few minutes, and then whenever the satellite is in this state, it just wants to survive. The next mode is detumbling, which will, the satellite will enter basically whenever there's too much spinning. There's a lot more to it than that, but basically that's what it means. And the satellite will try to correct itself, get to the correct orientation, and then after that, it can go into the next 3 states. I'll start with communication. That's when it will attempt to downlink any data. If the OBC has any on hand, that can only be done, of course, when the ground station is in range. The next state is the science state. This one can only be done for a very short amount of time, and this would be more of Shane's domain, where the instrument will start collecting the data, sending it to the OBC, and like what I explained on the last slide, the OBC will process the data into a more refined state, save it on the SD card, where it will eventually be ready to be downlinked when in the communication state. And finally, we have the idle state, which is basically whenever none of the other conditions are met. And
so now I'd like to speak on our electrical power system. In terms of our electrical power system in a general sense, I had already spoken on this, but we use I2C communication as we're using a Clyde Space-based electrical power system alongside a Clyde Space-based battery. The foundation of our electrical power system and communication alongside the battery is telecommands and telemetry. Telecommands are the foundation of commanding the electrical power system, and it's based on write commands and read commands. The write commands establish events, so they're basically actions to tell the electrical power system to do, or requests, basically getters or setters or actions. Read commands return resultants of the given events that are sent. So if we are capable of reading any data, we can run a read command following a write command and receive data. Telemetry is data that enables us to monitor the continual operations of the EPS. Specifically, it allows the OBC to do so. So prior to integrating our electrical power system into the EnduroSat software development kit and the generic driver that it holds, I wanted to ensure that the Clyde Space electrical power system was functional and the commanding was actually operational. To do so, I created a UI interface that we were able to use to force the onboard computer to command the electrical power system. By doing so, we were able to understand if the onboard computer could actually command this electrical power system and if the I2C network was functional. Some of this functionality testing started with a baseline of checking the board status of the electrical power system to see if we were at a good state and if the board status had no errors. Then we moved on to checking the manual reset count. This was just simple testing just to see if everything was good. So we wanted to make sure it started with 0, of course, because there was no manual resets on the factory electrical power system. Then we incremented this and just kind of checked to make sure it was incrementing properly. Following this, we went to more action testing. So we powered on the PDUs, or the power distribution units, and we checked the voltages and currents to make sure they're proper for the 3.3 volt rail, the 5 volt rail, and the 12 volt rail. We checked this via telemetry readings, so we actually asked the electrical power system to see if they were powered on and to make sure that the voltages and currents were proper. But to ensure this was actually true and that it wasn't just providing us this data, we also used a multimeter to physically check the voltages and currents, and we're able to affirm that the readings were proper. So following this testing, I worked on the actual integration of working the Clyde Space electrical power system into the EnduroSat SDK generic EPS driver, which is based on the ISIS electrical power system, if you're familiar. So what I started with, it was very simple. I mapped the Clyde Space commands to the EnduroSat commands because being different companies, they had different commands for their byte assignments. Following this, I removed any unsupported functions that Clyde Space didn't utilize that EnduroSat had included in their driver, just because it was unnecessary code that we didn't need. And then I added functionality that we would need for our Clyde Space electrical power system. For our Clyde Space electrical power system, it doesn't include a PIU, so for ISIS electrical power system, this is a power integrated unit mainboard, which basically has an automated action of collecting housekeeping data. This includes board status, PDU status, PCU status, just general information about the electrical power system to make sure operations are good. Since this wasn't automatically done, I had to manually create a driver that would collect this data by sending a housekeeping command that was supported by CubeSpace. So I would have a multitude of commands be sent through I2C, collect them, put them through an intermediate buffer, and then stuff them into the correct data member, and then return it to the OBC so it had the right information. Finally, we couldn't just rely on communicating with just the electrical power system exclusively because we wanted daughter board information from our battery. The electrical power system unfortunately couldn't provide this information with the telecommands that we had accessible. Therefore, I had to make it so that way we could communicate with the battery, which has its own I2C address, as I mentioned prior, and gather this information. So this was the daughter board temperature and status information for the battery. Thank you. Any questions?
Thank you.
You mentioned the SD card earlier on in the slides, and I wondered if we had some concerns about that some years back. But do you have any concerns about that card in a radiation environment being affected?
Yes, I've heard of people above me talking about that, but I'm just like, you know, a code monkey. Yeah, that is a concern, though. I can tell you that. And if you wanted to get into contact with us, we can get you into contact with someone who can definitely answer that.
Okay, thank you. Yeah, I was just curious because when we looked at it a few years back, and that things might have changed, that you know something. So, thank you.
How long did it take to sort out those compatibility issues between client and SDK?
That was pretty brief. It only took, because it's alongside my coursework that I'm doing this, it was very much longer than I would have appreciated it to be. It probably took a few months because alongside that, we had to get our software development kit working initially, and unfortunately with compatibility issues with our IDE version, that took way longer than it was supposed to, and then we finally found that out, so it took a bit long. Any other questions? Could you repeat that, please? Sorry.
I can answer that. So I think from what I know, we have different versions for the engineering models, and then we'll have a flat set at each of the campuses, and then when we construct the flight model, we'll have new EPS and not OBCs.
If that's it, thank you for your time.
Thank you.
Thank you.
Thank you. Next, I would like to welcome Alex Mariano from Bronco Space at Cal Poly Pomona.
All right. Hello, everyone. I'm Alex. I am a software engineer from Bronco Space, Cal Poly Pomona. And today I'm going to be talking about a preliminary implementation of the F-Prime software for managing machine learning applications. All right. I can't advance load. Oh, there we go. Okay, So just briefly about Bronco Space, we are an undergraduate research team in Cal Poly Pomona. Most of us are undergraduates. We do have a few postgraduates. We are founded in 2019, and also we started from a very simple idea and a hopeful wish to go to space, and we made it happen. So we launched 4 satellites into space, and we have now became the cutting-edge space technology program on campus. We also have several projects funded by NASA, and we have been able to push out developments and switch to RTR levels from 3 to 6 in a relatively short amount of time. Some of the testing that we have done here at Cal Poly Pomona is we try to outsource our testing as well as build in-house testing environments to replicate the harsh environment of space. So this would be like radiation testing, vibration testing. We would work with other universities and also build our in-house labs to conduct these tests. We would also build our own vehicles. So we actually create our own weather balloons and balloon launch vehicles so that we could test satellites in suborbital climates. And also we go to suborbital rocket providers to test out our technologies there. Additionally, we do have experience with orbital launches. As we said, we launched 4 satellites since the beginning of our program, and this is how we are able to get the full pipeline from designing a satellite, building, testing, and launching, and maintaining a satellite. So the full life cycle of the satellite, we gain that knowledge, and we are able to apply it for new upcoming satellites and other developments that we have at the lab. Next slide, please. Oh, there we go. OK, so Bronco Space satellites, we do try to create educational satellites. Most of them are very cheap and simple, and they are getting even cheaper and even more simple and fast to integrate and to test and to launch with every iteration. And I guess to go with the Bronco Space motto is we're trying to create a satellite that is an educational tool to bring from universities to have like just to have a feel for space and to like learn more about the space environment, what it takes to build a satellite and get something of a deployment onto space. And part of that into making a satellite is we want to focus on making a robust software. And this is where we look into multiple software for our use cases. So for example, we have the Orasat from Portland State University, our own Pi-cubed proofs kit from Bronco Space Laboratory in Pomona, and also the Artemis CubeSat from the University of Hawaii. Each of these satellites have created their own flight software. And of course, if everybody knows, flight software is really difficult to build and to maintain, to test, and to verify. And that's kind of the things that are going with these satellites is that you either could have like a really high cost but resilient software, or you could have low cost, but it is very fast, very cheap, low cost software. And you can have like a mix of the two and hopefully get F-prime deployment on satellite. So this is what Scales is trying to do, is we're trying to create a new flight software framework so that it would be like more robust and also be able to handle any satellite needs. Basically, it's a system that would manage models. I should mention. Scales is a spacecraft communications automation leading and edge computing system. It's supposed to be robust, adaptable, and rapidly deployable flight framework for implementing machine learning and artificial intelligence models. This system would maintain these models, and it would create a safe environment for these models to function, to train, to test, and also to execute their code. This is the path towards creating a safe, robust flight software so that it would be easier to deploy satellites into space. So the reason why we're creating this is because just the growing market of small satellites. So since the history of satellites, more than 2,300 small satellites, like CubeSat satellites, have launched worldwide. And they are compact and they are very cost efficient. And because they are cost efficient, most most industry and satellite developers are willing to take more risks and more experimental challenges to put into their satellite and test out new technologies. And they're basically like the new testbed for future space technologies. And this is why we need small sats, because they are the pathway to new technology. And of course, with these small satellites, there are obvious challenges with them. And one, with their compact size, you can't really put high gain antennas onto a small satellite. These antennas are usually large, and if you're going into maybe deep space, you would usually need like a huge dish, and that's usually not available for small satellites. And then also with the cost, if you're trying to create a budget satellite, you would also have to require to make a smaller operational team than a fully fledged like 12-unit satellite, which would, of course, it would bring down costs, but also it would, like managing that satellite would be difficult from the operations perspective. So these requirements require us to make a framework that would address these challenges with as little downside as possible. And this is the Scale's mission. Scale's mission is to be an integration between commercial off-the-shelf parts and also using a trusted software so that it could maintain, that enhances on-orbit computing and also improves reliability and mission assurance. So this would be working with the Jet Propulsion Laboratory with their F-Prime small-scale flight software group, and we would be working with F-Prime and to deploy it onto something similar to like an NVIDIA Jetson, and would be able to create flight software in an environment that would handle machine learning models for that. And the reason why we want to have machine learning models on spacecraft is, first off, just like for background, there's not many machine learning models right now on spacecraft. They're usually too risky and also too experimental. And that's why we would like to introduce them on spacecraft. And these are some of the projects that we have put machine learning models on in our lab at Pomona. So Bronco Ember is a autonomous wildfire detection unit. Moonfall is a lunar topography mapper. And also, we also have autonomous satellites. So this would be like a use case for autonomous navigation, collision avoidance, or even just earth sciences. Autonomous image capturing. And then I'll just go over it real quick. Bronco Ember is wildfire detection. It uses computer vision and also machine learning algorithms to detect wildfires, as well as make a prediction model about where these wildfires spread or how the smoke looks, so that firefighters on the ground would be able to know about a fire in real time. And part of the challenges of this is specifically the real-time aspect of it. Running this detection software on remote platforms is hugely beneficial. And if we get real-time data, then firefighters on the ground or any units in the air would be able to know about these dangers as quickly as possible. However, from our experience on our test flight in last May, a downlink of images are very costly. This is where from our test flight from last May, our weather balloon went outside of the range that it was supposed to, and we had to use the Iridium satellite network. And if anybody has experience using the Iridium satellite network, we only get kilobytes of speed of data. And it doesn't sound like a lot, and it's also definitely not a lot for imagery. So downloading one image would take minutes, maybe even an hour. And that way, we can't download all of our images onto a platform on the ground. And that would, of course, we can't train our model like that. But we could also send commands really quickly, since commands are generally like less than kilobytes. There may be even like less than 100 bytes of data to send a command. And also, the current implementation of Bronco Ember requires that like close monitoring and also model outputs as feedback. So these are actually trained model outputs from the wildfire detection unit, and this is something that we would have to train on the ground. We were able to retrieve this model, but in the event that we can't retrieve this model, we wouldn't have a model output. And then here's Moonfall. Moonfall is moon-fast and accurate LiDAR localization. Uses a combination of camera and LiDAR imagery to create a lunar topography of the map in the dark side of the moon. And, oh, there's a video. And then it uses rapid inferencing to try and tackle like craters or any like anomalies on the lunar surface that wouldn't really be captured by a high imaging orbiter. And for training this model used terabytes of data. So this used 200,000 images. Each are like 20 megapixel cameras and also LiDAR point clouds. And during our simulation tests, a 10-second lunar landing simulation used up 5 gigabytes of data. And that's just 10 seconds. So imagine if we have this running around or orbiting around the moon at a large scale. We wouldn't be able to download all of this imagery, and we wouldn't be able to download or downlink it and then train it. And that's the most problematic aspect of this is we need to figure out a way to train this in the machine itself rather than downlinking using a high-costly, high-bandwidth downlink system and also a computer on the ground. And this is where our system comes into play. We're using the F-Prime software framework to create a safe environment for machine learning algorithms to train and to test and to execute their code. Sorry. I can't see. But basically, this is supposed to be like the core functionalities of our flight software. We're basically trying to create a containerized unit so that so that we could have our machine learning models do their thing. And if they are, if everybody knows, like machine learning models aren't 100% accurate. There's only like an 80% or 90% confidence interval that they have. So in the event that machine learning models are out of bounds, for example, then the skills framework would immediately catch on that and wouldn't make a satellite ending mission right away. It would create some sort of path so that we wouldn't have to do a mission end because of an error in a machine learning algorithm. And then this is like going back to how most of our philosophy when we created the original proof system. It was a simple state machine. So basically, it's just a gigantic flow chart, and that's how the software was made. But the thing is that this software is very mission specific, and we cannot transfer it to other space missions. So every time we have to create something, make a new sensor, new implementations, or just have a generally new board, we would have to rewrite the entire software because the software is tailored to one specific board and one specific mission. And this requires a need for a reliable software that is easily deployable on and movable on any satellite missions. And yeah, and that's what Scales is trying to do, is try to create a deployable and movable, adaptable system. And part of the Scale system, as we done our talk yesterday, we are using something similar to an NVIDIA Jetson model, and this is where some of the benefits come from, is using like a Snapdragon, for example, would only give you like 4 images per second. You could inference that, whereas using an NVIDIA graphics card or NVIDIA CPU on an NVIDIA Jetson, you would be able to manage thousands of images per second. So it would be something that you would be able to train or into inference in the model on orbit. Great. That's the end of my slides. Thank you, everyone. Thank you for your time. And is there any questions? Oh, yes, please. Yes? Wait, sorry. What was your question? Yeah, so the wildfire detection model was pre-trained. Sorry, his question was if the wildfire model was pre-trained or not. And it was a pre-trained model, but when we get new imagery, we cannot really downlink that because of like the limitations of its the downlink system. So using the Iridium network and figuring out how to downlink all of the images. Sorry. Yes. Yeah, the downlinking of images allows us to retrain the model so that we can make the model better over many iterations. Great. Any other questions? Yes. Right. Sorry, I'm going to move this. Sorry, could you say it one more time? Ideally, the system would both be on F prime. So F prime has deployments for microprocessors as well as like an onboard computer, like an NVIDIA Jetson, and this kind of like helps like keep everything in a stable environment, and we would be able to have a computer that would work in space. Cool. Other questions? Yes. So are you asking how memory intensive it was for the models? Yeah, well, the model has to be on board in order to inference through it. And usually inferencing is really fast, but if we want to train the model further, then we would have to downlink the images and then train the model, uplink the model back onto the satellite, and then have the computer like inference based off that. But if we're downlinking many images, then that's not feasible. So if we don't have a downlink system or any system to manage the machine learning model, basically this machine learning model is stuck on the satellite, and it wouldn't be able to, you can't retrain it, or you can't do anything with it. It's basically just there, and it is a one-shot at inferencing. So then the scales framework is to create a model so that you could retrain it and you could get more data out of it. All right. All right. Thank you, everyone.
Thank you to Alex Marino. Next up, we have Brian Gunner and David Besson from Amazon Web Services, presenting Deploying and Optimizing Onboard Machine Learning Algorithms with Amazon Web Services.
Hi, good morning. I'm Brian Gunner. This is David Besson. We're with Amazon Web Services, Aerospace and Satellite Professional Services. So AWS is a provider for compute, database, storage, AI/ML, host of other services, all at customers of any scale. At Professional Services, we like to work hand in hand with our customers to help get everybody up to speed and really accelerate your journey in the cloud. And today we're going to be discussing how to deploy and optimize AI/ML models to the edge to your hardware devices. Okay, so first a little bit more about us. So at Aerospace and Satellite Professional Services, we really like to take on the undifferentiated heavy lifting, such as setting up cloud resources so that our customers can focus on what really matters, which is, excuse me, which is application development, their business logic, development of AI/ML models in this case. So with aerospace and satellite, we help out a lot of launch providers. We help out a lot of on-orbit customers. And this is kind of where this use case comes into play. We have a lot of on-orbit customers that are analyzing data from the Earth or elsewhere, using AI/ML to provide data classification. What is this? Is this a tree, a battleship, that sort of thing. So for our use case that we're going to cover today, what we're doing is we're collecting images through a camera. We're processing the data using AI/ML inference on board our remote device. And then the processed image is going to have a series of bounding boxes which are labeled, hopefully classified correctly with the different objects that it's detected. We're going to be using this I'll cover the tech stack a little bit more in depth, but we're using AWS Greengrass to deploy these models in this case, we're using an AWS Deep Racer. So an AWS Deep Racer is like a robotic car. It's like a scaled down version of a car with onboard compute. So we're just using that because we could bring it on stage. And in real life, what's applicable to you is we can use this on fleets of devices such as CubeSats. So the CubeSat constellation is perfectly analogous to this. Also keep in mind, while we're using AI/ML, specifically optimizing our AI/ML model and updating our model on the CubeSat, this could be used for a variety of software processes, such as like OS patching or updating a software version, really to solve any problem you have with a large fleet of devices, such as a constellation. How do we synchronously and consistently deploy our software models? Once you scale up and have a lot of CubeSats, this becomes a lot of issues. And this is a mature product because on the terrestrial, we're managing millions of devices using this same platform. So before I turn it over to David, I'll just cover our tech stack. The first thing that we're using is a Cloud Development Kit, also known as CDK. So CDK allows you to write your infrastructure as code in your favorite programming language. Infrastructure as code is super important because it allows you to define your cloud resources in a safe and consistent manner. It's much better than just going in the console and turning on and off services. Second service we're using, I kind of touched on already, and David's going to talk a lot more about, is AWS IoT Greengrass. So this allows you to manage a fleet of devices, each device running a component of software. And the next thing is TensorFlow, which is our open source, not our, but it's just a open source AI/ML framework, which is used globally. It's very mature. And then finally we have Onyx, which is another open source tool which allows you to define AI/ML models, and also used pretty extensively in the AI/ML world. So with that, I'll turn it over to David, who'll actually go into the use case.
All right. Good morning, everybody. Thanks again for having us. We were here 2 years ago, so see a few familiar faces, so great to be back. So with what we actually built for this, it's largely based on some resources we'll show you at the end of the presentation, which are publicly accessible. We have QR codes. They're easy to look up. They have the CDK code that Brian mentioned, so you can deploy a similar architecture, just opening up an AWS account. But we have done some tailoring to make this more applicable for the space domain use case that Brian just covered. So working from left to right through this very high-level architecture diagram, we have the developer working on his or her local computer. That's what has the CDK Python code in this case, which has been hooked up with secure authentication methods to the AWS cloud, like their specific account that we're using for this example. Using that CDK, you can deploy the core AWS resources that are used for the rest of the project. So the big SageMaker instances, which is the name of our machine learning service, the identity and access management relationships that allow all these things to communicate securely in the cloud, and then the resources that allow you to eventually deploy the software onto the robotic device or edge device. There is a step that you need to do to authenticate the car or vehicle as well. We'll show you the car towards the end of the presentation. That's what allows you to make the over-the-air updates in the future. So you only have to physically or through a SSH session connect to the car once. After that, you can do everything else over the air through whatever method you want to use to make a TCP/IP connection in this case. We could really drill down on this connectivity part, but the scope of our presentation is machine learning. So if you're interested in the former, talk to us after, and we can do more on that. The center part of the diagram is the machine learning building and training process. So again, we're using TensorFlow for the base framework, and then a specific TensorFlow model that's provided through the SageMaker Jumpstart hub. So you don't even have to know how the model works. You can just look at a gallery of them and say, oh, this is the one that's most applicable to my use case, and it's the right size that I need. It's been used in other projects. You can look through those and then just start using it. And then finally, after you update the model, you do subsequent deployments onto the device over the air. This is the really interesting part of the project to me. This is how you actually customize the model. So the model we're starting with, I'll show you on the next slide, is a generic object detection and classification model. It's used for everyday objects, not very applicable to space things. And so we added space things and trained it how to look for those. So again, starting with the developer computer, you take training images, you upload those to the cloud. We have a service that makes it very easy to annotate them. So this is how you turn them into raw images, into annotated images that can be actually used by the training workflow. SageMaker does the heavy lifting, so you're just running the super powerful, GPU instance for, in our case, an hour, and then it shuts down. You don't have to keep it running all the time, but this configures that process for you. You can also use a Jupyter notebook for the orchestration steps. And then finally, you update the very few updated resources to the edge device to make this work. So you don't have to redeploy everything. It's just the Onyx model that Brian mentioned. That is what allows the device to make the inference predictions on what it's seeing. So it's trying to make as few moving parts as possible for this workflow, right? There's a lot of complicated stuff involved, but people have already figured it out. You don't need to do that yourself. This is to try to help make it step-by-step, kind of cookie-cutter process so you can focus on the use case and not all this crazy machine learning stuff going on behind the scenes. So again, original model, it's trained on something called the COCO image data set, which is 80 everyday objects, including umbrellas and chairs. So it's a little hard to see, but they're outlined umbrellas and chairs in that sample image. And so you just feed in JPEG images. They can be any size. The inference model chews through it using deep neural networks, convolutional neural networks, stuff. Again, you don't need to understand to actually implement all this. And then the output are the bounding boxes, like coordinates in the image where the objects are, labels for them, and then the confidence score of how confident the algorithm is that the object is what it thinks it is. The fine-tuned model is exactly the same except for the final layer of the deep neural network. This is called transfer learning. So what you can do here is take a bunch of training images, run them through the training algorithm, use the same core model, and it just fine-tunes the last step. So it says, instead of these 80 everyday objects, now I'm just looking for 4, Earth, astronaut, spacecraft, and flag. So now we can find these things in the new images that we're uploading. OK. What did we use for training images? There's a very cool website maintained by Arizona State University and Johnson Space Center where they scanned the physical Apollo program film to make high-definition captures of all the images. And so there's about like 20,000. Most of them are just of the moon, which is cool, but not very helpful for this. So we went through and for Apollo 11 and 12 got 300 images that had the things that we were looking for. And here, there's a video showing in excruciating real time what's involved in annotating this stuff. So you can see you're clicking on a label, drawing it around what's in the image, and then when it's done, there's one more. You click submit. There's a tiny American flag on the lander. And then the result of that after each image is a JSON object, and that's what contains the training information I talked about before. You do that a few hundred times, and now you have a training set. So this could be a fun activity for your team, right? Like do a pizza party, watch a movie, and then just label stuff for hours. And then the end result goes in an S3 bucket, simple storage service to store all this stuff. And that's set up out of the box to work with SageMaker with the configurations we set up earlier. If this doesn't sound super intuitive, after all like the machine learning terminology, at the end of the day, this is what we're trying to do. The machine learning algorithm is drawing boxes on things it sees with confidence scores, like I mentioned. So if you look at the top 100 after you've fed the model or the image in, most of them are like OK, but there's a lot of noise. Like it's saying like I'm not positive that this one is it. But then as we filter down to only the most confident images, you can see it's getting more confident, more confident. And then in this case, the 2 labels are correct. So astronaut, flag, Earth, and spacecraft. OK, now we can show the car, I guess. So those were kind of pristine operating environments still working in the cloud. But now we want to actually deploy it onto the device to see if it works. And so could not get travel approved to go to the moon, obviously. So next best thing, just using my desk. These are things that the model has never seen before, right? Like this was trained from original images that were on the moon. But now we're applying it to these new shapes, photons, eventually electrons, pixels. And it's saying, like, can I tell what these are based on those things that you've already given me? And so in this case, labels are a little small to see. It does get the astronaut correct. It thinks its hand is the Earth. Kind of looks like clouds, so maybe understandable. It gets the flag correct, but then it says the blue sky and white clouds is Earth, which is kind of wrong because it's not planet Earth, but it is Earth, so we can still give it credit for that. Right, OK. And then this is what we're deploying it onto, right? So this is what we're trying to do to be kind of analogous to CubeSats. Kind of similar form factor. This is essentially like a Raspberry Pi with independent suspension and like big motors. There's a lot of really cool open source projects you can do with this. You can do a service in the cloud called Deep Racer, which shows you how to make autonomous racing circuits and use that. So if you want to get into robotics plus the cloud, this is a great entry point. But in general, you can deploy this onto anything, like an actual Raspberry Pi, or whatever you're using for your onboard hardware. And there's compute hardware. And there's a lot of documentation within the Greengrass service that explains how to do this on different types of hardware architectures. And the camera we used is just a simple USB webcam. This is nothing fancy. And so this is the baseline functionality, but you could keep expanding this with additional components besides the machine learning algorithm itself. So if you wanted to crop images, right, based on what you found and only download those, if you want to do like autonomous vehicle decisions, that it's like, oh, there's something coming at me that I don't like, I should turn around, something like that. Like you can keep building on this using the same framework, including other things from presentations you're seeing today, right? Like we're not trying to say this is how you have to do everything. We're trying to say this is how you can make things compatible with each other. OK, we can just show this off there, I guess. OK. All right, now the dessert course. Everybody loves Gen AI these days. How can you use Gen AI with this? Well, you can make new images from scratch, right? So this image is not based on directly the training set that I made. This is purely one of our Gen AI models on the Amazon Bedrock service. And so we gave it the sentence on the bottom, astronaut on the moon planting a flag in front of lunar lander with Earth in the background. And this is what it made. I guess it thought the moon is really important, so it made it twice. But again, we'll let it slide. You know, Gen AI is still a growing field. But this is really important, right? You can make new training images without physically working with like real-world objects. You can keep doing this, iterating on it, use that to refine the actual model, update what's on the edge device with the further optimized model, so then you can download better images and just like keep the flywheel going and keep optimizing everything across the board. And again, there's like little red bounding boxes. It does get astronaut, Earth, spacecraft, but it doesn't get the flag. So again, probably usually in machine learning, the answer is more data, right? You can try to be as big brain, smart math as you want. Usually the answer is more data. So if we just, instead of 300 images, if we did 1,000, probably get some better performance. These are the resources that I mentioned. I think this video will be up on YouTube and the slides, so if you want to go back and click the links or scan the QR codes later, you can. Top left, Greengrass V2 workshop. So this is the onboard runtime environment that I mentioned. This shows you how to set that up. SageMaker, machine learning in general. Getting started with AWS ML Edge. This is how you combine the two to do inference on devices like we use. And then if you actually want to get the car that we showed here, there's a link to do that and how to use the autonomous driving use cases and a lot of other cool code repositories through there. OK, so that's all we had for today. I think we have a couple minutes for questions. Thanks. Yes, in the back by the door. Yeah.
When images are taken from space, they may have distortion or cracks. Is it possible when even if image has distortion?
Yeah, that's a great question. So there's one thing you can do is just try with the default model that you've built if it can do it. Also, during the training process, instead of using just the actual images, you can artificially add distortions that would be similar to what you would see in the real operating environment. And so that's called augmented training. And sometimes it's used anyway just to boost your training numbers. Like you can mirror images, you can add grain, do black and white or color, vice versa. So that's a great question. You can definitely build up performance in that area. And then someone else had a question up here. No? Yeah.
So what kind of onboard hardware or CPU you require?
Oh, good question. So the car itself has 4 gigabytes of memory, 32 gigabyte hard drive. I can't remember which processor it uses, but that's on the high end, right, for what you do on a CubeSat. But this Greengrass service works with very, very simple devices, like what you would use for monitoring temperature with a wall socket sensor. So very minimal footprint. So you would probably have to work backwards and say, what's the smallest I could make my model? And there are options that have very lightweight. There's a model even called YOLO, you only look once. And so that one is smaller because it's not doing as many convolution steps. So it's hard to answer the question directly, but there are methods to iteratively reduce the performance footprint of the model. Do you have any other ideas on that?
Yeah, I mean, I'll just add that the Greengrass documentation is pretty extensive. It'll lay out the minimum requirements, and obviously you'd need to have enough compute and storage on your device to store the actual AI model, which for inference isn't that bad. We're doing all the training in the cloud, but as long as you have enough compute to handle inference, which is not that difficult, you should be good. So probably have to tweak it on the ground, obviously. So.
Okay, I think we're out of time.
Yep.
All right, thank you.
Thanks, everybody.
Thank you. Unfortunately, our 11:20 presenter is unable to present, so I'm going to kindly ask Mateo from Deorbit, if you're in the audience, please head backstage and we can have you present early. But up next, I would like you to join me in welcoming Rudy DeRose and Dr. Samson Fan from NASA's Flight Opportunities Program and the Small Spacecraft Technology Program.
All right, good morning. I'm Rudy DeRose from the Small Spacecraft Technology Program.
And I'm Samson Fan from the same office.
And we're going to talk to you about how at NASA we're trying to enable and leverage industry to advance small satellite technologies. All right, so we're doing this presentation on behalf of two NASA special programs. There's the Flight Opportunities Program, which is led out of Armstrong Flight Research Center, and the Small Spacecraft Technology Program, which is led out of Ames Research Center. So the Flight Opportunities Program aims to demonstrate promising new technologies and expand space commerce through the use of commercially procured suborbital flight vehicles. And then the Small Spacecraft Technology Program aims to advance small spacecraft technologies in particular. So the two programs are complementary, and we work very closely together to help increase TRL of technologies. And we recently put together an IDIQ mechanism to procure on a rapid pace suborbital and hosted orbital flight opportunities. All right. So just focusing a little bit more on the Small Spacecraft Technology Program. We try to achieve advancements through target development and frequent in-space testing, so to reduce the cost of spacecraft missions, reduce the amount of time that is necessary to develop them, enable new architectures, increase their capabilities, as well as augment existing architectures with small satellites as much as possible. All right, so how do we do this? In practical terms, we have together, both programs, we have a host of different, whole bunch of different mechanisms that we use to address different segments of the industry, whether that be academia or small businesses, and we target different TRL levels with these different mechanisms. The majority of these are recurring solicitations, and so that focus on specific NASA technology gaps. So I recommend you go on the TechPort website here on the QR code, and you can go and see how your technology might fit in the NASA landscape and which solicitation might be most appropriate for your technology. So I'm just going to run briefly over some of these. So we have University Small Sat Technology Partnerships that caters to universities, and Sam is going to go in more detail about that. We also make extensive use of SBIRs. We have, for example, the tech flights, so where we fund researchers to go and develop, to go acquire suborbital flights to increase the TRL of their technologies. And then we also have a prize format, the Tech Leap Prize, to address specific NASA challenge. And then we also work with other programs like the CubeSat Launch Initiative and the STMD Tipping Point Awards and ACOs to increase when those are related to small sats. And then if you're already working with NASA, there may be an opportunity to set up flights of opportunity, missions of opportunity with us if it makes technological sense and there's funding for that. So for that, you should go and talk to your NASA funding organization, and they can come and talk to us. With that, I hand it over to Sam to go over USTPs.
Awesome. Thank you, Rudy, and thank you all for attending this talk. I'm really excited to be talking to you guys about the University Small Sat Technology Partnerships, or USTP. The key focus of this partnership is to advance technologies that are being developed at the university level and get them to fulfill technology shortfalls both within the small sat industry as well as within NASA. And so we understand that the heart of the innovation economy is here at universities, and we want to tap into that so that we can fill those technology shortfalls that we're seeing in the community. At the same time, we recognize that a lot of universities around the United States don't have a lot of experience developing spaceflight technology hardware. And so that's where that partnership between the university and NASA comes into play. We get to share our relevant experiences with you folks in order to help advance your technology. Now, a lot of NASA's experience in spaceflight has to do with these multi-billion-dollar missions or safety critical human space exploration programs. And so there's a different philosophy when it comes to risk, cost, and schedule relationships there. And so this is a two-way street for both you guys to learn how spaceflight technology development is being done at NASA, as well as for us to learn from you guys on how do we develop on programs in which risk, cost, and schedule have a different relationship between what we're traditionally used to. And so, as with everything that NASA is trying to do, we're keen on educating the next generation of innovators. And this particular program is focused on developing innovation and the innovators within the small sat community. The last two bullet points here kind of highlights the benefits that the two parties can get. NASA will benefit from the innovations that you guys are developing. The universities will gain experience on developing spaceflight hardware. So this slide here talks a little bit more about the nitty-gritty details of the partnership. It's a 2-year university-led cooperative agreement between the principal investigator at the university, usually a professor or a research scientist, as well as a NASA center or JPL. And the key to this cooperative agreement is identifying a key technology that is of mutual interest within the small spacecraft community that we're trying to develop. And we're talking about small spacecraft here. We're looking at technology specifically on the order of 180 kilograms or less directed to those systems. The university obtains about $225,000 a year in funding in order to support the development. They're also able to obtain about half the time of a civil servant at NASA in order to help guide the development process. The NASA Center also is allowed to access a pool of funding up to $30,000 a year in order to address hardware purchases or services that they may need in order to help assist the university. So I want to remind you that this is a cooperative agreement between the university and the NASA Center. And we're looking at technologies which are at the TRL 3 to 5 level. The USTP program is geared towards helping those technologies kind of bridge that, what people call the valley of death, in order to get to the TRL 6 level. That's our main goal, so that you guys can go on a follow-on NASA program or another opportunity in order to get you guys a flight demonstration. USTP is a competitive solicitation, and so the topic at which the solicitation addresses also varies from year to year. At the very bottom of this screen here shows the topics that we addressed in the USTP 2023 cohort. We're looking at GPS independent position, navigation, and timing technologies, edge computing, as well as thermal control for small satellite systems. And at the very bottom is a list of all the universities which participated in the 2023 cohort. So one of the measures of successes for our program is for these technologies to get a flight demonstration. And this is just a highlight of some of the universities that we've worked with in the past. So first is Montana State University. They are developing radiation-tolerant hardware for space applications. And they advanced through our USTP program followed by flight opportunities. And since then, that technology has been picked up by the CubeSat Launch Initiative, demonstrated on board the ISS, as well as being picked up by the Commercial Lunar Payloads Services Program. So a very successful cooperative agreement there. Stanford and NASA Ames partnered to develop swarm constellation technologies. They had a balloon flight and an orbital demonstration in 2021, and another orbital demonstration at the beginning of 2024. And I understand Zach Manchester may be talking about this latest development at a later talk. And San Diego State University, a very interesting project. They were leveraging commercial 5G technology in order to develop networking technology for applications in the lunar environment. And they have a up-and-coming high-altitude balloon flight. The last university project that I'll talk about is one with the University of Texas at Austin. And they were primarily focused on software, developing a computer vision-based method of surface navigation for lunar applications. They also have an upcoming flight. So the ability for USTP and I guess other programs as well to make flight opportunities possible, flight demonstrations possible, is through a close partnership with our Flight Opportunities Program as well as with commercial vendors. And so the IDIQ that Rudy was talking about earlier really allows us to access these flight capabilities. Rocket-powered vehicles for suborbital launches. This is procured from Blue Origin as well as Virgin. We are also able to provide USTP cohort participants with high-altitude balloon flights, as well as the infamous parabolic microgravity flights as well. One of the more, I think, interesting opportunities out there include the vertical takeoff and vertical landing vehicle opportunities that your technology may participate in. A new capability that's coming online is that of hosted orbital payloads. I'm particularly interested in this because it allows you innovators to focus on the key technology that you guys are trying to develop. The things like comms, power, thermal control, all of that development is offloaded towards the host. And so with that, I'll hand it over back to Rudy.
All right, thank you very much, Sam. So in addition to what Sam covered, it's very important for us also to support the flight test community. And so we've put together a community of practice that hosts regular webinars the first Wednesday of every month, where we invite researchers to go and present the technologies that they've flown and any lessons learned that they might have. And so we also have a newsletter, so you can go and sign up at the link there, that covers anything pertinent to the flight test community. So that could be the upcoming solicitations, the webinars, as well as any other resources. And so this we launched 6 months ago. We also launched the Lessons Learned Library. So here we pull all the resources and organize them per the phase that you might be in. So if you're working on the proposal, then you can go and find all the resources we have, the webinars related to that. Or if you're on the payload design, you go in that section. And so this is still a work in progress, but we hope that it will be useful to the community. All right, so we hope to be able to work with you to develop new small sat technologies. You can come and talk to us at the booth, the one at the NASA booth, the one with all the models. You can also go and visit our websites here or contact us at our email address here. And with that, that's the end of our presentation. So thank you for your time, and I think we can take questions. Sure, go ahead.
For USTP, does that come out under ROSES, and is it annual or semi-annual?
USCP is highly dependent on the funding that is provided, and so the desire is to have it on a yearly cadence. However, depending on funding, we may or may not release one.
When is the next one?
We're actively working the process right now, and so I can't give you an exact date, but you know, through your usual NASA solicitation sources, you know, please be on the lookout.
All right, so another question there.
Could you speak a little bit more to that valley of death that you mentioned before? Because I'm wondering what the #1 reason why university CubeSats don't get off the ground.
Yeah, sure. In one particular lens, it has a lot to do with funding availability. When you're at TRL 1 to 3, the funding requirements are typically pretty low, and there's usually enough funding there to get you to that point. On the other side of that valley of death is TRL 6 and onwards, in which you're just about ready to demonstrate that technology. All you need is a little bit more funding in order to, get on that rocket. The hardening and the development to make the system rigorous enough to survive and to be deployed on a satellite system or on a rocket, that's the part where it's a little bit tricky to obtain funding. And so one of the things that we're trying to do is to bring technologies that are just sitting on that cusp and to bring it over to the other side so that they can access flight opportunities, they can access CSLI, other things that may get them to orbit or to whatever relevant environment they need.
All right, any other questions? One more, go ahead.
The participants from the cohort, the 23 cohort, are they all more or less guaranteed to make it to CSLI or not necessarily?
So these are partnership programs. We tend to talk very frequently with CSLI and the flight opportunities people, but it is not a guaranteed entrance. Having support and demonstrated capabilities through our program definitely helps in your resume and your proposal to the next stage.
All right, well, one more question, yeah, go ahead.
On an earlier slide, mentioned, I forget which program, but Montana University had done some study of radiation-tolerant flight computers. Are these results from anything that you've worked, are they available publicly, or is that something that's held by them?
I think, so one of the things that we encourage in our program is for these results to be published. And so I haven't taken a direct look, but I'm relatively confident that you might be able to find the results of their flight demonstrations somewhere in a journal.
All right, any other questions? All right, no? All right, well, thank you very much for your time. Much appreciated.
Thank you.
All right, so I have a couple announcements. First off, you may have noticed on the schedule there's a career fair scheduled for tomorrow, sort of 10 a.m., 10:30 to 12:30. This is the first time we'll have done the career fair. So what we're looking for, it's going to be more of a one-on-one arrangement. We'll give you specific logistical information tomorrow. But if you're a student here, be on the lookout for an email asking if you want to participate, because it's more of a one-on-one. We need an accurate count, and so there'll be an email that goes out sometime today to ask about that. Just be on the lookout for that. The other thing is we still haven't been able to locate Mateo, so his talk is still scheduled at 11:40, which means you have about 19 minutes to enjoy guilt-free use of all your electronics without taking away from the presenter, and we'll be back here at 11:40 with Mateo. So you have a short, quick break.
shall find that our so-called civilization was gloriously destroyed by a handful of vacuum tubes and transistors. Who would ever have believed that human beings would be stupid enough to blow themselves off the face of the earth?
Thank you for your patience. We will now be resuming with our presentations. I'd like to welcome Matteo Lorenzoni from Deorbit, presenting In Orbit Now, in-orbit transportation services for satellites and responsive hosted payload IOD.
Whoa, whoa. There's so many people. So, good morning, everybody. I am Matteo Andreas Lorenzoni. I am the head of sales of Deorbit. Deorbit is a company which is based in Italy with subsidiaries in UK, Portugal, and a small one in the US for commercial purposes. Deorbit has the vision to enable the space logistic in the next years. And next years means 10, 20, 30, 40. So what we really want to do is to enable the market to be ready to take advantage of all the opportunities that space can provide. We want to do this. As of today, we are working on commercial services that I will present very shortly. In the next few years, we would like to start providing services in terms of in-orbit logistics, such as refueling of other satellites or helping other satellites to leave the orbit. So we want to take care of the full life cycle of a space mission, from the launch to all the activities that can happen in orbit. And on the long vision, we would like to start taking care of everything that can happen in space, such, for instance, space recycling, space manufacturing, so that we can save the time and money to go from Earth to space. But now that I talked about the long vision, let me focus on the short vision of what we are doing today. So our first step in the space logistic are the launch services. So we are here because we take care of launching CubeSats and microsats. We can support during the whole mission to go from Earth to space. If you have a 1U, 2U, 3U, 6U, 12U, 16U, 8Us, whatever you have, we can take care of all the logistics that brings your satellite from Earth to space. We do this collaborating with space launchers like, for instance, SpaceX, Vega, Rocket Lab, and we can support in all the phases that are due to get your satellites to space. We started from this because this is, in our opinion, the first step in the space logistic. For instance, at some point realize, okay, if you want to launch one CubeSat, you can be okay with the rideshare orbit that is proposed by the launch provider. But what if your experiment your CubeSat needs to go to a very specific orbit? How do you do? Can you purchase a dedicated launch? We said, maybe it's a bit expensive. So that's why we start building Ion Satellite Carrier. Ion is a rideshare platform, is a satellite built in Italy, and the target is to be able to bring CubeSat to specific orbits so that they can optimize their mission according to the final orbit they can reach. To explain you better how Ion works, just start imagining that you have a constellation of satellites. You want to launch maybe 8 6Us. If you want to launch 8 6Us, probably you can go, as I mentioned before, on a standard launch service, and then release all of them and waiting for each satellite to reach the exact position in orbit, or you can put them on Ion. We can, with Ion, perform several maneuvers, one of which is the altitude raise. So maybe you need to reach to 600 kilometers because you want your life longer, or maybe you want to go to 400 kilometers because for some other reason for Earth observation is much easier. We start performing maneuver, and we can release the satellites in a specific altitude so that your mission is much more effective. Once we get to the right orbit, we just don't release all the satellites all together, but we start make the phasing so that the time to business of your constellation is much, much faster. And as I said before, imagine to have 8 satellites. So maybe you want to release 4 and ascertain ascending node, but then the other 4 you want to release in another ascending node so that we can start the maneuvering of run shift so that we can release and phase again the other part of the constellation in a different orbit. The other value of doing these maneuvers are basically that with the altitude raise, for instance, you can reach specific orbits that you couldn't reach with a normal rideshare. With the ascending node change, with the run shift, we can provide the opportunity to get to 2 orbits with one single launch, bringing a lot of improvement to the mission in terms of time and in terms of money. And the phasing, as well as time, is the most important thing in a space mission. We know you don't have to wait the differential drag to have all the satellite phased along the orbit, but we can do that. So rather than months, we take it in weeks. And we pretty much said, we have seen in the past that we are able to reduce up to the 80% the time of deploying a whole constellation along the same orbit. This is just an example of our first mission, just for saying that we already tested these. You can see on the left the standard deployment. This launch happened on September 3rd of 2020, where the customer was Planet Labs. They put some of the satellites on Aviga, and then they put the other satellites on Ion. On the left, you can see after 2 months how the satellites that have been released directly from the Viga, you can see the position. While on the right, you can see the position of the satellites that were released and deployed by our orbital transfer vehicle. You can see the difference between the two, and it explains by itself. These images instead is something that I always show when I used to present, because I know that the quality is not that high, but this is very important because we have been the first company to release one satellite from another satellite, and we've also been able to take a picture of it. And this is the picture of the first satellite that we have been able to release since our first mission. Now, I didn't see before, but Deorbit is a B Corp. B Corp means that we really take care of the environment and of the sustainability. So this means that after that we perform these missions and we release all the CubeSat, we don't want to just deorbit the satellite and trash this beauty. What we want to do is to give it a second life. And we can give a second life just giving another sense to the mission. And therefore, we started to provide servicing for in-orbit servicing, for in-orbit demonstration, and in-orbit validation. This means that on Ion, as it is a satellite and it has its own resources, such as power, downlink, uplink, memory, we can put directly the experiment. So you, for instance, want to test an antenna, radio, any kind of sensor, whatever, literally everything. You need to build a satellite. This takes time, this takes money, and this is something that will be a debris, unfortunately, one day. So what we instead decided to do is to give our resources to your experiments, to the experiments that we can host, so that we can operate the payload that we have on board our platform and provide the data to the end user. In this way, we tested before that we have been able to bring a test, an experiment in less than 6 months from the laboratory of our end user to space. This is an example of Drago 2, that is a payload from the Institute of Canary Islands. They didn't have time to build the CubeSat or the satellite to bring it to space. They just put the camera on our Ion, and those are the pictures that we took last year. Now, it's quite hard to recognize, but this is Colorado Springs, and we made it in the occasion of the symposium of last year. After that, we use Ion for all of these things, and I can really say that we have done it before. You can see here that we launched 15 missions. Other 3 or 4 are coming this year, and we are targeting to have up to 15 launches per year. So I'm talking about something that we have done before. Like, it's something that we do regularly. We are also thinking in the very close future to start using our constellation as a satellite as a service, so that people that need specific data doesn't need to build a satellite, but they just can ask us the kind of data that they need, because maybe for some reason we are already running that kind of mission and we are able to provide this data to them. Then also the satellite for rent. As I mentioned before, we can put payload on Ion, but we can also provide the service of operating them so that we reduce the number of satellites in space. And as third things, which I believe will be one of the best things that can happen in the space, is this cloud computing. Because through the cloud computing, and probably some of my colleagues already said in some past presentation, can really change the world, because we can reduce the amount of data to download, and we can make the calculation and the elaboration of data directly in orbit, so that we can reduce the amount of data to download, and so that we can also accelerate the time in which data can be available to ground. And the application of these are infinite, and I guess that you know almost better than me. And with these, guys, I thank you so much for your attention. I try to keep it short because I know that you're starving. It's lunchtime. And if you have any questions, I'm here to reply. Okay, so let's first thank you. So for the downlink, we work pretty much with all the ground stations that are available. We use Amazon Web Service, we use Leaf Space, so that we can have access to all the ground station on ground. At the moment, we work through an S-band, so the capabilities that we showed so far is about 4 mega per day, but now from the next mission, we are getting to 1 giga per day as a download capabilities. Is this replying your question? Any other question? Thank you.
Thank you, Matteo. We will now be going on an hour break and returning at 1 p.m. for more presentations. Lunch is provided for you right outside the main lobby and the entrance of this building. Please enjoy, and we will see you at 1, where we will hear from NASA's CubeSat Launch Initiative. Thank you.
Welcome back, everyone. First up, I'd like to welcome Craig Raffington from the NASA CubeSat Launch Initiative.
All right, good afternoon, everybody. Craig Raffington. I am with NASA's Launch Services Program. So we're the program that launches all non-crewed missions, or your scientific, planetary, all of that stuff. That's what we do. I'm going to be going over the CubeSat Launch Initiative update for 2024. My compadre, the fellow mission manager, Norman Phelps, is in the front row. Zalimi. We have another mission manager that couldn't make it. All right, that is our mission statement up there. So basically what we do is feed the STEM pipeline. In a nutshell, that's what we're doing. Since this program started in 2011, we've had 3,600 students or so pass through the program. So we're doing our part to keep that workforce primed. Accomplishments today, 200 plus distinct teams selected, 162 CubeSats launched. Over the past year, we have done 5 launches. The most recent one was Alana 51. That was deployed from the ISS last week, actually. And we got confirmation yesterday that the final team made contact, so we're all good to go. Special shout out to Big Red Sat. They're the first team selected from from the state of Nebraska. So the next year, our busiest year ever for CSLI. We're going to do 10 launches, over 30 CubeSats we're going to launch. I was at Vandenberg, meeting my team earlier this week for the integration of some of the CubeSats in Alana, 43. That integration is going to be ongoing all week, so it's going to be a busy year for us. All right, congratulations to all the team that made it for Call 15. Some amazing science, just astounding. Dapper, I got to give a special shout out. They're first team selected from Delaware. All right. Nyansat Oakwood School, that's a high school in Northern California, or wherever that Bay Area is. Just amazing seeing students, high school students, build satellites. And Pleiades for the other Cal Poly. I don't know how you call yourself, the other Cal Poly, but 6-1Us, and I saw them outside building something. I'm like, that's just amazing. That's commitment. So kudos to you guys. All right, this is our tally of where we've launched from. California, you guys are dominating, 43. I don't know what you guys are doing. Whatever you're eating, keep doing it. 43 is you're just blowing everybody else out of the water. So good job. Next states that even come close are 14 apiece. So. Now, one of the things I want to bring up, the states that's the white colored ones, you got your South Carolina, North Carolina, Mississippi, Oklahoma, looks like South Dakota, Wyoming, and Nevada. You've never been in the program before. If you're a representative, student, and from that state, we would love to get you in the program. Stop by our booth. We'd love to get you in. So how do you get in CSLI? Eligibility, there's 2 appendices, Appendix A and Appendix B. Appendix A is for your schools and nonprofits, and that's U.S. institutions. And Appendix B is for NASA, JPL internal for early career. And we define early career as within 10 years of getting your degree or 3 years of switching a discipline. So how to join CSLI? All right, so your first step is to develop your idea. If you're a school student, go talk to your faculty, get your great idea. Second step is to build your team. It has to be student-led and student-ran, it has to be. But you also have to have faculty advisors. Secure funding. We will pay to launch you. We will not pay to build your satellite, but we will pay to launch you. My bad there. You got the merit and feasibility review that must be done. And then the last thing is to apply. The call comes out every August, and we close it every November. So one of the questions I get quite a bit, I was at a conference last month, and a bunch of students have come in to me asking if it's a competition. The CubeSat Launch Initiative is not a competition. Absolutely is not. If you follow the directions in the application of the scoring rubric and your science is good, there's a high probability that you will get in. You know, they don't give us a quota. We can let in 0 teams, 10 teams, 20 teams. It's not a competition. Just follow the rubric, and it's not that big of a document. This year it was only 25 pages. It's an easy read. All right. The science is up to you. We don't tell you what your science should be. 100% up to you. But when you're starting out, your best friend is going to be the CubeSat design specification. I think they're at Rev 14. The more unique and weird things you put in there, the harder is it going to be for us to get you a ride. So be very cognizant of the safety requirements. There is a waiver process, but the more waivers we do, the harder things are going to be. Somebody might not even want you on their rocket. So just be mindful of that. You need versus you want. This is important. However much you think it's going to cost to build your CubeSat, it's probably going to cost more. Things aren't going to work. Things are going to break. I've seen a high school do a CubeSat for $26,000. I've seen a couple universities that were well-funded. They had really good donors, or generous donors. I shouldn't say good donors. And they spent over $2 million a piece on their CubeSats. Most of the CubeSats that we see in the program are coming in between $50,000 and $200,000. So that's the range where most of the colleges are. And it's not just about your financial budget, it's your energy budget. How big of a solar panel do you need? Take the time up front and work all of these things because it's going to come back later on to haunt you if you don't. All right, project management and communication. Young engineers are famous for absolutely wanting not to do paperwork. I understand. You want to get in there, you want to get your hands dirty, you want to see stuff work. I get it. I made the same mistakes way back in the 90s or whenever I started. So it's understandable. But you know, system engineering, failure mode analysis, project managers, basic communications, just please pay attention to that stuff. We got a call, I want to say a couple months ago, from a team that said they're not going to be able to make their mission. We're like, okay, thought it was supply chain issues or something. No. What happens is that the students, the seniors on the team graduated, and the team, I don't know if they were freshmen or whatever that came in, they didn't know how to turn on the CubeSat. Something that simple, 0 documentation. You know, something that trivial as documentation can just derail your project. So don't ignore it. And it doesn't have to be fancy, but don't ignore documentation. So words of the wise, be flexible with your manifesting option. Be compatible with many dispensers. I mentioned the CubeSat design specification before. I'm going to tell you to read it, know it, and love it. I'm not going to say caress it, but just really get to know that document. It's going to really save you a lot of pain. Be flexible with your orbit requirements. The more unique your orbit is, the harder it's going to be for us to find your ride. That's just the bottom line. And you can look out there in industry and you see where you see where we're going. You see where transporter is going, bandwagon. We can take you to the ISS really, really easy. Yeah, we have to supply that constantly. We have partnership with the Department of Defense, and sometimes they give us rides, sometimes we give them rides. But there's options, but if your orbit is too unique, it's going to be challenging to find your ride. So the $300,000 that I mentioned, we will provide up to $300,000 to launch you, and that's typically enough for a 3U. Not only do we pay to launch you, but within that, we also pay for an integration contractor to help you along. Choose a unique name, be consistent. You might have your name spelled one way on the FCC document, another way in ODAR, another way in your NOAA, and these various organizations are going to look at it like it's a different CubeSat, even though it's the same one. So just changing something simple on your name technically changes what CubeSat it is, so just be mindful of that. Communicate with LSP about any hazardous material. If you just tell us up front, then we can work it. I don't know what a provocative feature is, so we don't want your CubeSats twerking in space. I don't know what that means. We might take that word out of the presentation. So designed to pacify CubeSat at the end of the mission. That's an important one. That's the last one I'm going to touch on this slide. But something that's not on the slide is the FCC 5-year deorbit rule. There's some CubeSats we have in the pipeline from before, and we're meeting with the FCC on a monthly basis to try to see how we're going to work that out. But hey, it's 2 government agencies working together. You know how one work by themselves, so we don't know where that's going to end up. So keep you guys appraised of what's going on with that. All right, tips on licensing. Start early and be persistent. This is very important again. I told you we were down at Vandenberg earlier this week integrating some CubeSats. There's 2 CubeSats we will not be able to integrate. So what we're doing, we're pushing them off to the last minute to see if we can get them on the ride. They don't have their FCC license. If they don't get it, we cannot integrate them, we cannot launch them. We're going to have to launch some dummies, if you want to call it that. And it's just a waste of money launching simulators, mass simulators. It's a waste of money. And it's a waste of opportunity for another team that could have used that spot. So another thing with licensing, it's just paperwork, not fun, not sexy, but we have to do it. Some reference information up here on the big screen, and I believe all these slides and the presentation is going to be available to everybody, so information is up there, but it's you're going to find it online too. And with that, this is the name of the mission managers, or contact information. I mean, feel free to reach out to us at any time, and we will respond to you. With that, do you guys have any questions? No? All right. So we have a booth outside, so please stop by, talk to us. We love talking to you, so take care, y'all.
Thank you, Craig Raffington. I'd like to now introduce Charlene Nazari, Andres Cuevas, and Matthew Casillas from Cal Poly Pomona about additive manufacturing and developing a universal CubeSat technology testbed.
All right, hello everyone. We are CubeStep, which stands for CubeSat Technology Exploration Project. Today we are presenting on the role of additive manufacturing in creating a universal bus. My name is Charlene. I'm the current project manager.
I'm Matthew Casillas, and I'm part of the structures team.
My name is Andres Cuevas, and I'm the systems lead.
So a little introduction to CubeStep. We are a multidisciplinary collaborative project between Cal Poly Pomona and NASA JPL. We are part of the JPL University Crowdsourcing Initiative, known as JUICY, and our project began in spring 2020. So our project has 3 main objectives. The first is to design and develop a universal testbed for technology readiness level maturation. The second is to utilize additive manufacturing in integrating and designing custom structures and technologies. And our third main objective is to design, develop, and test a oscillating heat pipe, or OHP. So onto our concept of a universal testbed. Our testbed refers to the CubeSat itself, the bus structure, as well as the avionics that house, power, and protect the payload. Onto a universal testbed, what we mean by this is creating a bus that is capable of integrating any technology as a payload. As a kind of standardized and economic platform to integrate these technologies to rapidly increase their TRL by testing them in the space environment. And additive manufacturing is a very powerful tool in creating this universal testbed because it allows us to develop complex geometries and integrate them directly into the bus structure. So an example of a complex geometry is the image shown. It is an oscillating heat pipe with an integrated battery case. As you can see by the blue channels, those are the channels for the working fluid. And this is something that would be very costly and complex to machine, but can be easily 3D printed. This is actually the first payload that CubeStep has worked on, collaboratively designed with JPL technologists. We have since transitioned to a more basic form of the OHP technology, just so we can characterize the OHP in the space environment in its kind of most simple form before applying what we learned to this battery case. So moving on to some of the high-level requirements we had in developing a universal testbed. These are overarching requirements kept pretty general to accommodate for the wide variety of technologies we want to be able to integrate. So these include being able to operate in the low Earth orbit, since a majority of CubeSat missions take place here. Being equipped with a dedicated flight software system that has to be modular. There will be more on this later. Utilizing commercial off-the-shelf components in order to decrease the cost and lead time associated with making them ourselves, as well as providing the structure for the payload and being able to communicate with a ground station while in low Earth orbit. So on to our higher level hardware requirements. These include being able to compile, store, and manage payload data while in low Earth orbit, using solar panels to generate power for the CubeSat and for the mission, and testing the payload. Solar panels, since they are the most economic and widely available option for power generation for CubeSats, as well as having 3-axis stabilization, being able to distribute the generated power to all components, as well as being able to send and receive commands from the ground station. So there are some challenges in creating a common bus, since it has to be capable of integrating any technology, which can be a very daunting task. In the context of CubeStep, we have a 3U bus as shown, consisting of a 1.5U half for avionics, 1.5U for payload, and we want to be able to integrate any technology so long as it's within 1 to 1.5U in size. So some challenges with this mainly are the interfaces, namely the mechanical interface, such as securing the payload and the effects of this on mass properties. Electrical interfaces, such as feeding wiring through the bus system, as well as data due to the varying capabilities of different technologies and the radically different data that they collect, produce, and output. Another challenge is also the flight software and keeping it modular so that it is able to interact with any technology. CubeStep's approach to this so far is we are using the F-Prime framework developed by NASA, and we are essentially modeling the payload as a black box in the software, like developing the software assuming we don't know what the payload is. So what is the impact of additive manufacturing on design, especially in the context of a universal bus? So additive manufacturing, when it is used in design, the printer capabilities must be at the forefront of your mind when designing. Some main issues you could encounter are issues with having to take care of print orientation. So as an object is being 3D printed, gravitational effects can cause deformations. So print orientation is something to consider as you're designing. Another thing to consider is the need for support structures as the items being printed. And another factor is the size of the structure you want to print, which will be limited by the printer print bed itself. An advantage that additive manufacturing brings to designing, especially a universal bus, is that it can help to integrate payloads directly into the bus structure, which can solve the issue of how you will insert different technologies, as well as being able to create complex geometries that might be very costly or difficult to machine. Again, an example is the battery case with the capillaries.
Okay, so common materials used in additive manufacturing are typically like aluminum alloys, such as 6061 and aluminum alloy 7075. And the type of methodology we're planning on using in terms of 3D printing for our bus structure is powder bed fusion, which essentially is just a fine layer of the powder that we're using, spread it across the print bed that's already on top of a preheated metal substrate. And essentially that powder is then lasered from the 3D printer, and it is essentially from the scanned, which is scanned accordingly from the predefined slice pattern essentially. And this process is then repeated layer by layer until the structure is completed. And it's also worth mentioning that there are some post-processing for 3D printing. And as seen in the image here, you can see that there's residual powders left from the 3D printing process. So an additional post-processing is needed to remove those residual powders, essentially. And also in terms of the surface roughness, is not at the same level as traditional manufacturing. So additional surface machining is needed to meet the requirements of our mission. And now in terms of heat treatments are typically a favor to increase specific types of mechanical properties for the structure after it's been 3D printed. And also it could help reduce the porosity levels from the print structure. And also the impact of additive manufacturing in terms of integration, it can allow the ability to essentially print the payload and the structure simultaneously. And as you can see in the image here, the battery case and the bus structure were actually printed at the same time. And this also allows for a unique quality where the OHP walls actually are exposed to the space environment, so that actually acts as a heat sink as well. And now in terms of the bus interfaces, we decided to use 4 key locking inserts, also known as key inserts. And they are bonded to the bottom Z face of the OHP half of the bus. And the corresponding other half is accompanied with the appropriate Allen head fasteners to then join both 1.5U bus structures. And also it's worth mentioning that the key locking insert placements were actually also 3D printed into the additively manufactured structure as well. And in terms of our 3D design and how we plan on printing it for our flat plate OHPs, they will be oriented vertically, since as seen in the image here, depending on the orientation the structure is printed at, it can affect the actual structure from the forces due to gravity could affect or deform some components in the build process. And in terms of like the OHP channels, if we were to print them horizontally, we would need to compensate that by printing the OHP channels instead of a circular shape. We would need to make them more of like a teardrop shape to account for gravity. So that's why it's important to understand the orientation that the structure's in to avoid any issues during the printing process. And that's also for in terms of overhangs as well. It's great to avoid overhangs greater than 45 degrees, since it can kind of cause like maybe errors or deformations during the printing process. Although for some structures that do have overhang, like the thermal reservoir OHP that we'll show later, structures are needed, and it can help build the structure during the additive manufacturing process. And also it's worth mentioning that depending on how accurate the printer is, we have to constrain the OHP channel diameters and radius turns to to fit those requirements from the specific printers we're using.
Okay, so here's an image of a work breakdown structure of our high-level system design. So you see we have 3 segments, one being the bus, and under this segment we have all of our avionics and our structure. I'll go through them quickly. We have the EnduraSat onboard computer with GNSS, the EnduraSat EPS2 with included battery pack, the TensorTech Magnetorquer attitude determination and control system, and the EnduraSat UHF transceiver and antenna. In our payload section, we have the 3 OHPs, which I will go into in later slides, thermistors to record the thermal data on the OHPs, patch heaters to heat up the evaporator section, and a data acquisition system to ensure that the data from the thermistors is collected and sent to the onboard computer. We also have a ground station segment that has an antenna controller, and a transceiver to communicate with the satellite. So here's our bus capability, and this is dependent on the boards that we selected. For our EnduraSat boards, this gives us an available average power of 10 watts from the solar panels, a battery capacity of about 42 watt hours, power buses including 3 volt, 5 volt, and 12 volt, an onboard computer with an ARM Cortex M7 chip and 2 megabytes of flash storage, up to 480 megahertz clock speed, and a micro SD card slot for expandable storage. This gives us also a data rate of up to 100, telemetry data rate up to 100 kilobits per second, and a payload data rate of up to 125 megabits per second. And one thing I want to note about the data interfaces, one of the main challenges that we have in designing a universal bus are the varied type and number of data interfaces available on certain components. So to try and solve this issue, we decided to get as many components for our avionics from the same manufacturer as possible to ensure that we can know that all of the components are compatible with each other. So that's why our data interfaces are so varied and also so numerous. Finally, our attitude control system is the TensorTech Magnetorquer control system, which has a pointing accuracy of 5 degrees in the sunlight and a slew rate of 1 degree per second. So here's an image of our current bus structure design. You see on the left-hand side of the image, we have the bottom half of the 1.5U bus housing the avionics. In the middle, you can see the key inserts design, as well as the OHPs that will be mounted onto the bus. And then on the right-hand side of the image, we have the top 1.5U half that houses the payloads. So quickly, I want to explain kind of the concept behind these OHPs. So you see on the top right image, there's a heating section that will evaporate the working fluid inside of the OHP, creating vapor plugs that are sandwiched by liquid slugs. And these will oscillate through the channels through the adiabatic section into the cooling section. And then the vapor plugs will recondense back into a liquid. And these phase changes facilitate higher heat transfer than the parent material. And in the context of the battery case, it can also help mitigate thermal runaway of individual batteries and help prevent it from spreading to the other batteries. However, like Charlene and Matthew have noted on previous slides, we are stepping away from this design for now to focus on simpler versions of this OHP concept in order to characterize this new technology, which we can then use to go back to the battery case and optimize it further. So speaking of these new OHPs, we have 3, which is why we call this payload CubeStep Cerberus. The first one is just a plain, passive, flat plate OHP with a patch heater for the evaporator section, and it also will have channels, obviously running along the plate. And one thing to note on all of these designs, on the right hand, there is currently a fill port to insert the working fluid inside of the channels. And on the left-hand side, we have 2 ports for removing the excess powder that is left after print, but those will be removed in the final designs. We also have a check valve OHP. This one is very similar to the passive OHP with an additional check valve to help increase the time or decrease the time it takes to reach steady state operation. We also have a thermal reservoir OHP that has an additional reservoir of working fluid, and this allows for variability in the conductance that the OHP can reach, depending on how hot or what the temperature of the OHP is. So here's a quick overview of our concept of operations. Our launch vehicle and deployment mechanisms are still to be determined. However, after we deploy, we'll have a delay before activating our radio frequency components, dependent on the launch provider. It could be about 2 minutes. Then we'll enter it into our detumbling sequence, which could last up to 12 hours. And then we can deploy our antenna and calibrate our communication subsystem. Then we can wait for our batteries to charge and receive commands from the ground station planned to be hosted here at Cal Poly SLO. Then we can begin our main mission, going through our testing cycle, and finally naturally deorbit within the required 25 years. So going over our testing concept of operations, we have a testing power range of 5 to 45 watts with 5-watt test increments. And at that 45-watt mark, our minimum test duration is 38 minutes long. Our period of orbit is going to be about 90 minutes with an eclipse period of about 34 to 35 minutes. And it takes about 55 minutes to charge the batteries to full from an 80% depth of discharge. And our ground station contact duration will be about 5 to 6 minutes per contact event. In conclusion, additive manufacturing is a critical and useful tool in designing and creating a universal testbed because it enables the design of complex geometries and allows for diverse technologies to be integrated directly into the bus and tested. There are challenges to be overcome, like the design of mechanical, electrical, and data interfaces, and having a modular flight software. So the next steps for our project are we will have a PDR at the end of this semester, and then move into manufacturing the OHPs and the structure next summer. In fall of 2024, we will begin to test the OHPs and the structures. And in spring of 2025, we can begin integration of the structure, OHP, and avionics boards, hopefully setting us up for a launch in fall of 2025. And then once we get the data back from these 3 OHPs, we can use that to further optimize the battery case and return to that in spring of 2026. That is it. Thank you for listening. And if we can field a few questions if we have time for a few. Yes.
How do you remove the powder from the OHP channels after the print is finished?
So after the print is finished, they use the powder removal ports. I'm not 100% sure about the process of how those powder removal ports are used. I just know they use those ports.
Yes. Yeah. Yeah. How much does it cost?
Well, it depends what you're printing. I don't know. I think for the battery case, one print was $10,000. So it was pretty expensive.
Yes. I'm sorry, what was the question? How do we create the loop in the battery case? I'm sorry, I don't think I understand the question. How did we fix the loop?
Like, I think maybe how are they manufactured? So actually the loops themselves are just kind of hollow. So as it's printing, it just doesn't print in those areas. So basically prints around the loop, if that makes sense.
Yes. You have omnidirectional antenna. Yes. Why do you wait 12 hours until you deploy the antenna? Just because we want to make sure we have enough power in the batteries to ensure idle operation before we begin testing. More questions? Okay, thank you.
Thank you,
Sorry,
everyone.
we're out of time. Thank you.
Thank you to Charlene, Andres, and Matthew. Next up, I'd like to welcome Jackie Gwynn from the United States Naval Academy, presenting warm isostatic press for additively manufactured ABS outgassing reduction in CubeSats.
Okay, so good afternoon, everyone. My name is Midshipman First Class Jackie Gwynn. In case you couldn't tell, I'm at the Naval Academy. And I'm here to talk about a post-processing method for a potential reduction in outgassing for additively manufactured products on CubeSats. So the motivation behind this, I think we can all agree, and we've seen throughout this conference, that additive manufacturing is increasingly popular in CubeSats. And it's being used not only for educational purposes, but also for real-world applications in space. Additive manufacturing is popular and advantageous for a multitude of reasons, including cost effectiveness and lightweight capabilities, as well as the complex geometries capable through additive manufacturing. A key player for my research is that the cost effectiveness of it makes it more accessible for universities and small budgeted groups, which helps people with smaller budgets get into space. So there's a multitude of different techniques for additive manufacturing. One that's been used before in CubeSats is selective laser sintering. The advantage of selective laser sintering is that it does produce very high quality parts. However, the equipment used to use this technique can be quite expensive, and it's not readily available at all universities and, as I said, smaller budgeted groups. A popular material for SLS is called WinForm XT. This has actually been used at the Naval Academy. If you heard the RSAT presentation yesterday, they use WinForm XT for the robotic arms on their CubeSat. Another type of additive manufacturing, however, is fused deposition modeling, or FDM. This method is probably more popular. It requires less expensive materials and less expensive equipment. So this is more readily available at a larger range of groups trying to get into space. However, it does have some imperfections and some downsides presented with FDM, and we'll get a little bit more into that. So just going into how FDM works, basically we use a round filament. This is typically for plastics. The round filament is pushed through a heating element and deposited onto a build plate, which then creates the part in a layer by layer, bottom to top method. One of the more common materials for FDM is called ABS, or acrylonitrile butadiene styrene. This material is commonly used, again, because it's low cost, and we've used it at our school as well as many universities around the world. The problem with FDM, though, is that when we create using this round filament, it creates what we call microvoids, or simply air gaps, in between the layers of the filament. So if you can imagine two round like rows of filament next to each other, there's going to be some air pockets in between, and that can lead to decreased structural properties as well as the potential for outgassing. So outgassing, if you're not familiar, is the concept of gas inside of a part. When it gets into the vacuum environment and the space environment, that gas being released from the spacecraft can cause contamination and other harmful effects with your spacecraft. The problem is, if we use FDM, there's been some preliminary research to suggest that FDM can increase the risk of outgassing, and what we're trying to do is keep FDM and ABS specifically, keep that possible and feasible for space. So what are the different ways that we can improve the additively manufactured part using post-processing methods to make it more space feasible? So some initial scanning electron microscopy into an additively manufactured part shows us the microvoids here. We saw that especially in areas between where rows of filament change their orientation, here we use a cylindrical sample, and on the outside edge of it, where it switches from a vertical to kind of the circumference of the sample, you can see more pronounced are the microvoids in the air gaps produced in those additively manufactured parts. On the right side of the picture, you can also see there's microvoids just in between the layers, between specific rows, and also between layers in the vertical direction as well. So this is what we're trying to reduce through our post-processing method. The solution that's been presented through some other preliminary research is called a warm isostatic press. The idea behind this is that we apply high heat and high pressure to a product that's already been additively manufactured, and that will help basically condense that part and reduce the microvoids and get the air pockets to be basically removed from the part. I'm basically trying to replicate some prior research that's been conducted already in a university setting. And what we've found is that you can see at the bottom the importance of vacuum packing. So the idea is in the center picture, if you don't vacuum pack your part, we introduce the risk of actually, under high pressure, actually putting air into the part. So a key step was making sure we vacuum packed the sample before we conducted the warm isostatic press in order to make sure the air actually leaves the part and doesn't get forced inside. After a lot of design iterations, we finally came upon this final design for the warm isostatic press. In order to achieve the pressure that we needed in an omnidirectional manner, we decided to use just a standard nitrogen gas tank. These are nominally held at 2200 psi, and we were looking for something slightly less, so we used a pressure regulator to get the pressure that we were hoping to use for the warm isostatic press. And then on the right side of the picture, you can see our whip chamber, which is really just a pressure chamber that would house the whip sample, and there would be a heating element on the outside of the whip chamber to basically achieve the temperature that we were looking for. Overall, this warm isostatic press process would actually take 1 hour, so we would get the heat that we were looking for, maintain that 100 degrees Celsius, and then apply pressure, hold this for an hour, and then reduce the pressure and the heat, and see what happened with our part on the outside. On the left picture, you can see that the left side is the heating element, just a standard heating controller from Par Instruments. And then on the right side of that picture is the actual heating machine. So inside of that is where the actual whip chamber is. And on the right picture, you can just see our nitrogen gas tank with the pressure regulator. Here you can see that we just vacuum sealed using a standard vacuum sealer each part. And in the middle, you can see the inside of our pressure chamber that we used. It was important that we filled the pressure chamber almost completely with water, just to leave, reducing the risk of any kind of catastrophic explosions. So just by having a small volume of air inside the chamber, if anything did happen to overpressurize and explode, we wouldn't have anything catastrophic happen in our chemistry lab. Finally, on the right, you can see the actual heating controller, all set up in the middle of a whip process. To optimize this process, we were sure about the temperature. 100 degrees Celsius is right around the glass transition temperature of ABS. However, we weren't sure what's the optimal pressure, what pressure do we actually need, and what minimum is really necessary to achieve this reducing of microvoids. So we conducted an experiment just using 2 different pressure categories, and that was 750 psi and 1300 psi. So after conducting a whip on multiple samples in each pressure category, we ran some additional scanning electron microscopy, and we found these results. So you can see with 750 psi, or our low pressure category, there still are microvoids in the part. So we weren't able to fully achieve the objective using our low pressure. I think you can see in 1300 psi, we were able to much better close those microvoids and reduce the air gaps by design, also increasing the density of our final part. Overall, samples with 1300 psi, on average, we found them to increase in density by 3.1%. So in conclusion, we found that this warm isostatic press process is in fact effective in closing the microvoids that are inherent in additively manufactured parts, specifically using fused deposition modeling. In the future, we're looking to find ways to make sure that we can preserve the shape and structure of those parts. In theory, if we were to use too high temperature or too much pressure, we do run the risk of actually just completely collapsing apart, and that kind of defeats the purpose of additive manufacturing in the first place. So we're definitely working on refining that process and making sure we can maintain the shape and structure of our parts, especially with internal geometries, which is part of what makes additive manufacturing so advantageous. Additionally, we are looking to actually quantify the effect of closing those microvoids and actually reducing the risk of outgassing. So this will most likely be through bake-out tests and finding more quantifiable data to confirm that our post-processing method can actually reduce the risk of outgassing and allow more additively manufactured parts, more low-budget projects to actually get into space and be space feasible. With that, I'll open the floor for questions. Yes.
So a common concern I'm aware with 3D printed parts is that the material is not very isotropic. Does this have the potential of increasing adhesion between the extruded filament to produce more isotropic material properties overall?
That's not something that we've actually looked into yet. I think that that honestly might depend on the specific filament that you use. Yes. So that's actually, that research on that is what brought me to this. So the research that gave me the preliminary design for the warm isostatic press, all of that research was specifically on increasing the mechanical properties of AM parts without any kind of CubeSat or space-related applications. So I took that research and that's how I brought it to CubeSats. Yes, if you, actually that is this park source. Yeah. Yes. Yes, so that's one of the key challenges that we ran into with preserving the internal geometries. So the parts that we used was a standard, just a cylinder, just to fit inside of our pressure chamber. But we also had a center slot removed from the center of the part. And on some cases, we did notice kind of a crushing of the inside of that sample. One thing that we tried to do was place a coin on either side to basically close off that center slot to hopefully reduce the collapsing. Didn't totally work, so that kind of led us to, this is where we need to continue working in the future. Yeah. Oh, yes. So that also came from the park, the primary or preliminary research that I got my idea off of. In their research, they used 40 bar, 50 bar, and then 90 bar, and they only saw really significant results with 90 bar. So that's how I got the 1300 PSI. Yes? I'm sorry? Oh, so it's not very noticeable. As I said, we experience increase in density by 3.1%. So it's not something that you would actually be able to see. What we plan to do in the future is basically seeing if, for example, holes for screws or any other kind of structural components of a CubeSat, if we were to do this post-processing method, is that going to significantly change the size of the holes to a point where we would, again, have to go back and do some more traditional manufacturing and machining on that final part, in which case it might not make additive manufacturing advantageous anymore. So our initial research has shown that the change in volume is very small, mostly because the size of microvoids, the total volume of microvoids is actually pretty small. Yeah.
Is it possible to remove the constraint of using the vacuum bag by using maybe a noble gas or something that wouldn't be a problem during outgassing? Or is that maybe not effective?
That's not something I've looked into yet. That's definitely an interesting concept. What we've done with this is tried to apply the additive manufacturing to a lot of different applications in addition to CubeSats. So the outgassing, I'm not totally sure if we were to use other gases. Yes. My initial guess would be no. Again, when we took measurements, we only noticed a change in volume through water displacement volume measurements. It was not something that we could have actually caught by, for example, using calipers or anything for more rudimentary volume measurements. So my initial guess would be no, it doesn't change the size and shape enough to significantly alter a fit check. Mm-hmm. Okay. Oh, sorry, one more.
Was the deformation in any way consistent or predictable?
The deformation, as I mentioned with the center slot, that was pretty consistent. We did notice that the center slot did slightly collapse for each sample. Other than that, we didn't notice any specific deformation on the outside of the sample or on the sample as a whole. So the data that we got as far as the standard deviation in increasing density was very low. So all the data we got was pretty consistent from sample to sample. In the future, it could be something that's actually quantifiable, and you could manufacture your parts and design them to actually account for the reduction that you would expect to happen through a warm isostatic press post-processing. Okay, thank you for your time.
Now, if you'll turn your attention to the screen, please, we have a message from our gold sponsor this year, Blue Canyon Technologies.
This is our home. One small speck, suspended in an endless sea of stars. Human curiosity compelled us to explore it and drives us to understand it. That's what keeps Blue Canyon Technologies at the forefront of innovation. We're a dedicated team, expanding the limits of science and defense, using end-to-end spacecraft solutions, industry-leading pointing accuracy, and the highest performing satellite components. Our systems span Earth orbits and are capable of reaching the deepest environments to propel us into the unknown, because the final frontier is only the beginning.
All right, I'd like to thank Blue Canyon again. Their sponsorship and support helps make this event possible. Unfortunately, our 2 p.m. speaker got sick this morning, is unable to make it, so we have no 2 p.m. speaker. The next talk will be at 2:20. And so we'll see you then. Thank you.
Hello, welcome back from the break. I would like to introduce our next speaker, Dr. Alexei Rakow from MMA Design, and he's presenting the low-profile CubeSat Solar Array Drive Assembly.
Okay, thank you. Very excited to be here, not least because I get to wear a microphone like this, which I've never had the opportunity to. This is fun. So I'm going to talk to you today about our new low-profile solar array drive. I'm calling it version 2.0. For those of you not familiar with MMA Design, we're in Louisville, Colorado. We're about a 50-person company that specializes in deployable space systems. I'll give an overview of some of those technologies here in a second. I wanted to acknowledge our team that worked on this effort. Madeline Pauly was really the lead behind most of this. She was the intended speaker. She couldn't make it today, so I'm presenting in her place. And then Austin, Brent, Andrew, and myself all contributed to this effort. So some more background about MMA Design. I'll go over our solar array technology. We have a lot of CubeSat solar arrays, but we also work on deployable antenna systems, membrane antennas. On the solar array side, we have mission Marco. We were the solar arrays on Marco that went out beyond Mars. BioSentinel that we heard about on Tuesday. Sunrise. I'll go over some of these programs here in more detail. This is just a background on kind of the evolution of MMA's solar arrays over the years. Sorry, this is an eye chart, hard to read, but back in 2010, there's a 1x3U footprint solar array with a solar array drive assembly. I don't think people can see it there, but so you can kind of see we went from 1x3U to 6U form factors, and then out to larger form factors. I think on Monday, the notion in the keynote there, I said Monday again, Tuesday, with Dr. P's talk was how this sort of evolution has played out. It has for us in many ways, starting small and then growing to larger scales. So this is a table that you can also find on our website. I'm not going to go through all this, but we have 1x3, 2x3, 2x4U footprint wings, and we also have some larger wings that are going on ESPA-sized spacecraft as well now. In addition to kind of our standard HAWC, so HAWC arrays, that stands for high watts per kilogram. We have what we call optimized HAWC arrays, which have improved packing efficiency of cells on the surface, and that increases our overall power by on the order of 20, in some cases 30%. So there are many configurations that you see listed here to achieve target power. I wanted to show a few of the systems or the solar arrays that we've delivered to different CubeSats. Marco, as I mentioned, you can see a model of Marco out in the exhibition area at the NASA booth. These solar arrays deployed in 2 axes. You can see our arrays along the side of Marco there. This is a very cool picture with Marco passing, one of the Marco spacecraft passing and taking a picture of Mars there. So our array is here flipped out and then rotated and locked into position as you see there. There was no solar array drive in this case. Asteria is another program that we Made the solar arrays for this mission for NASA JPL. You can see the panel, or there were some body panels static in that system. And then this is an upcoming launch that we're excited about. Sunrise, this is a group of CubeSats that are going into a formation and forming an early warning system for solar flares. So I think this was shown in yesterday morning's talk about BioSentinel. This is another picture of that. Underneath the Orion capsule, the ring here had a total of 10 CubeSat dispensers. So that's another view of what we saw yesterday. This is just showing the concept of operations for our wings deploying from that spacecraft. We had 2 wings that were fixed that deployed out from the canister, and then the other wings had 1x3 footprints and restraints that were fired later. So I'll go over another image of BioSentinel with some more detail there. So on that Artemis mission, we had 4 CubeSats with our arrays in total. Unfortunately, NEA Scout was quote-unquote dead on arrival. At least the information that we have. I'm not sure if any communication was ever established with it. The rest of these have performed nominally and are out at the moon, so that's very exciting. And some other exciting programs that we're working on include this Spider Arachne program. This is from Air Force Research Lab, a 500-watt array on 4 panels, or we have PV on 3 of them. At MMA, we designed and built this deployable system, the launch restraint design, the PV layout, panels, all the rest of it, this entire deployable system. And this is being used for demonstrating space solar power, so converting solar energy through the PV side and converting it to microwave energy and beam to the ground. So exciting stuff. So here's BioSentinel again. I just wanted to point out there's that SATA that rotates these 2 panels. So that's a 2x1 footprint. This is some heritage SATA technology. And then here's some other examples of our SATAs on CubeSats. There is early stages 1x3 array with this 1U footprint thin SATA. And then we have a larger wing. This, I think, is like the Aquilius wing, with the SATA rotated 90 degrees. And then this is the SATA I was just talking about with that 1x2. This is just showing Lunamap, what we delivered there, SATA plus 4-panel wings. You can see it from the underside on the spacecraft. And this is just showing some examples of the deployment ConOps, how we fire our restraint, and in this case of the 1x3 U footprint, you can see how the panels unfold, and then we have the SATA rotation axis in that case there. Here with multiple panels, you can see how they unfold, and we're able to rotate them. This is a 112-watt deployed wing, and this is a 42-watt deployed wing, as you see pictured here. Okay, so that was kind of a background on our solar arrays in general. Now I'm going to talk about our SATA designs. The ones that I showed in the images there, as I mentioned, they've flown, they have flight heritage. We have gone through kind of a redevelopment of the SATA for an upcoming mission. That's in qual as we speak. So I'm calling it V2.0 here, new SATA. I'm sure we could come up with many different names for it. One of the big things we've done here is gone over to a rad-hard design with FPGA. We can also have lower cost rad-tolerant parts that are drop-in replacement. We've done a lot of work improving the wing mechanical interface, and I don't have it listed here, but a lot of work to improve the mechanical durability and reliability of our drivetrain. And then we have increased our software functionality. So we have a very tailorable acceleration profile and options for stepper mode or half or full stepping modes to increase torque depending on our needs. So these are some of the, Madeline put this table together. It kind of repeats a lot of the highlights that I had on the prior slide. We have increased safety limits, the drive mode flexibility, error reporting. So we made a lot of strides on the software, the electronics, and the system. So this is just a comparison, the interface and geometry of the what I'm calling original SATA or V1.0. And then this is our new design with, we have a different mounting interface that I'll show you in a second. And we did pick up some thickness in the assembly, but that has enabled us to put in a larger motor, which has enabled us to deploy and drive larger wings. I'll talk about that more in a second here. So here is just the form factor of the original version, 5 watts nominal, about 500 milliamps current draw, RS-422, and it's 9 millimeters thick. What we didn't like about this was the attachment for the yoke of a wing. We had a bonded pinned attachment there. We wanted to be able to detach the wing in our current design. So we've now have this configuration. This is a, This is a, the mounting flange for the wing, wire harness that can be connected to the wing. And we have grown from 9 millimeters to 12.5 millimeters. We're mounting with the pattern, the 440, or number 4 screws there. This is just showing how we interface to the spacecraft. We have alignment features there and wire egress through a pass-through and the bus wall. Pretty straightforward. And here again is just showing this new flange bolt-on configuration, so that enables us to take the wing on and off, which is very handy. And you can see those features captured there. So I mentioned that we picked up some thickness. What that has enabled us to do is put a larger stepper motor into the system. Currently, we are working in qualification on a system that's larger than any that we've had before on our SATAs. So that's what increased the thickness, was going to a larger motor. We're able to accommodate over 1 kilogram of deployed mass with our new SATA, and that's just for one wing. And just to give you an indication of increased torque, we're not talking about the output torque through our drivetrain ultimately. This is just listing the motor torque, just to give you an idea. We're at over 5x torque compared to the thin 7 millimeter and over twice, or not quite twice, with this new design compared to the 9 millimeter. I think, yeah, so before I conclude, So this is just a 3D printed version of that dual output 7mm design, and then here is a 3D printed mock-up of our, what I'm calling V2.0. If anyone wants to kind of get these in their hands and get a sense of the form factor that I'm talking about. But yeah, with that, thank you, and I will take any questions. I thought I saw, yep.
On the previous slide, you had a listing of the maximum mass that could be supported by the SATAs for a wing array.
Uh-huh.
I wanted to ask why the SATAs are limited to certain mass.
Yeah.
Is that more about
It's an excellent question.
inserted back into the SATA on the launch environment, or is it due to on-orbit operations?
Right. Yeah, so I don't know if everyone on the video cast can hear the question, but it's a question regarding this table. What limits us to that, or what is the interplay between the wing mass and the size that as listed there? So the inertia is part of it because we have to spin a larger mass at, to achieve the same rate. So having the higher torque is part of what's going on there. The other aspect, though, is the deployment loads that end up going back through our drivetrain. As you're deploying a larger wing that can have more dynamics and more torque that can be put back as like like an impulsive kind of load back into the drivetrain. So going to this new size, we've limited the torque that ends up back at our motor to a safe level for a over kilogram wing, if that makes sense. Is that clear now? Okay, good. All right. Any other questions? Yes.
How much full deployment testing are you able to do on the ground?
Yes, that's another good question. We do offloaded deployments of our arrays. I think, going through a typical acceptance test campaign for flight articles, they see a minimum, I think, of like 6, like a half dozen deployments. We've done, with the development of this, we've used an EDU wing, and just to kind of put it through its paces, because this was V2.0, we've done close to 20 deployments now. And so, yeah, that's where we're at right now. Yeah. Yeah, thanks. Okay, any other questions? I'm down to 1 minute. Nope. Okay, thank you.
Now, please welcome Bob Vermillion from the RMV Technology Group with his presentation, Can CubeSat ESD Qualification Testing with Sound Packaging Engineering Protocols Before Launch Ensure Successful Deployment for Space Survivability?
Everybody, it's great to be here. It's nice to see all of you here. Special welcome to the United States Naval Academy, Air Force Academy, and Coast Guard Academy. Nice to see our brothers and sisters here. My talk today is on ESD engineering compliance ensures successful CubeSat deployment. I'm located at NASA Ames Research Center, Moffett Field. My company is RMV Technology Group, and we're proud that we have the largest ESD lab located at a NASA center. First of all, I want to dedicate this presentation to to those who have served and made the ultimate sacrifice, United States Navy, the Army, Marine Corps, Air Force, Coast Guard, and to 3 astronauts that represent all the astronauts that have made the ultimate sacrifice: Gus Grissom, Roger Chaffee, and Ed White. Now, if it wasn't for Moore's law and microprocessor densification, we wouldn't have CubeSats. We're still in the vacuum tube technology days. So consequently, we are looking at, initially, behind Moore's law, microprocessors densifying or doubling every 2 years. However, today, both ESD-sensitive devices, such as commercial off-the-shelf or government off-the-shelf for space and defense, are sensitive to less than 50 volts. Doesn't take much to kill them anymore. ESD has found its way to CubeSats, touch displays, electronic wearables, and handheld devices. Represents about a $40 billion problem worldwide. Now, you can click this video later on, but this is a game changer. This ensures that Moore's law lives on. IBM, in cooperation with Samsung, were able to change the method of manufacturing for microprocessors on a silicon wafer in the vertical position. Therefore, they can stack and densify more, but they don't have the same current leakage as in the horizontal position. So, if we look at Moore's law, in 1971, the first microprocessor from Intel Corporation, the 4004, was equivalent to around 2,300 transistors. That was a big deal. In 2008, and I was with the Intel team consulting when they got the announcement that they had smashed through the 2 billion transistor equivalency mark for a microprocessor. Well, last year, Apple's M1 Ultra can claim 114 billion transistor equivalency. That's awesome. And let's put it in perspective with satellites. Like the GOES-R, for example, weighed 6,300 pounds. Huge aircraft carrier in space. And now, if we look at what's happened in recent years, the Laddie, 844 pounds, Cygnus 1, 64 pounds. Now we look at CubeSats, they're 3 pounds. But the way they build the cube in the circuit card assembly, and with the densification that's going to take place in the next 6 to 8 years, it's conceivably possible that a swarm of 5 or swarm of 6 CubeSats will have the same power as the traditional 2 or 2.5 ton satellite. So, what do we have to be concerned about? Well, with densification means there's no protection mechanisms. So the delivery package, which is the deployment cylinder or deployment rectangle, has to be able to shield. And also in the 0% relative humidity of space, when you have contact separation and it deploys out the tube, you don't want a field-induced model discharge to kill the components as they deploy. So we have to subject it, in this case, with this TU pod or cylinder CubeSat. We conducted resistance testing, electrostatic decay testing, and static shielding testing. So for flight, we want it to represent what the relative humidity in space would be when we test this out, which is 0%. However, let me go back here. The humidity controller only reached down to 0.2%. That's good enough to get going. So what we did, take a volume resistance using a concentric ring, measuring through to a base plate through the delivery door of the TU pod, and we want to know that if it has electrical conductivity in it. In this case, it's very conductive at 10 to the power of 3 ohms. So we go on to the next test. We still do volume resistance testing, and let me see. We'll look at the deployment door. So we're going to measure volume through the door, each element, and it's conductive. So for effective electrostatic shielding, it's something of this caliper and being bulk loaded, we have to be conceivably in the 10.3 range. Now, for flight, and we have the TU pod here, or the cylinder that's going to be used to deploy the 2 CubeSats, we test with a 2-point probe because of the irregular configuration, and in this case I use an electrometer, a Keithley, and we're in the 10 to the power of 3 range. So we're good. We're going good so far. Now, what I like to do is charge up the whole structure, including the inserted CubeSats, being 2, charge it up to plus or minus 1,000 volts, and see what the rate of decay will be, and it shall be decayed to plus or minus 100 or lower in less than 2.0 seconds. In this case, we add 0.02 in both cases. The next thing we did is we measure from the deployment door through the whole unit, and we had very fast decay, 0.06, 0.01. That ensures that when everything's put together, there's electrical conductivity. You need to check this out before things are deployed in space. Once you deploy into space, unlike an Apple computer, you can't issue a return material authorization. You know, they're not going to do what send another satellite up there, or we don't have shuttle capability to make the repair, and so we have to do our due diligence here. So we're going to test the material that we use to package the circuit card assembly and the TU pod, and also our work surface and such. So this is a static event detector. It represents an ESD sensitive device. Thing about it is it triggers red when it sees 100 volts, so you can reset it and use it over again. So I want to determine if this is going to survive a discharge, so I hit it with 5,000 volts using a simulator machine model discharge, more pronounced, and 10 discharges. And when I finished with the discharges, I see it still has the clear window inside. So it passed that phase at that location. But then I have to do this all over the tube, 10 discharges at 5 kV, and in all cases, it had a clear window. So is it going to survive EMI, RFI from space? You know, this is an indicator that it will help and assist that. So the deployment tube or deployment rectangle is a shielding package. It's an advanced shielding package. So in conclusion, sorry folks, deployment door volume resistance pass, 2-point resistance pass for the tube, volume resistance from deployment door to base pass, electrostatic decay from top to bottom passed, electrostatic decay from both CubeSat units to base passed, electrostatic decay from CubeSat inside TU pod through the spring and base passed, and it passed the Dr. Collier high voltage discharge test using the simulator. So, when we're building CubeSats or small sats, we have to have the right protocols in place so we don't kill it while we're building it. And in this case, this is at NASA Ames. This is where this system was built in my lab. And NASA likes to use overhead ionization or single fan ionization. That floods the area with positive and negative ions, which neutralize charge in case there's an outside charge source that comes into the area, even though someone's wearing a wrist strap and taking precaution. So in this case, Amin from Teton Aerospace is building, or his circuit card assembly and checking it out and conducting soldering. Why he's wearing a wrist strap? We have a monitor. The work surface has been verified that it not only has great resistance, but it doesn't charge generate. So if you move the circuit card and touch it with the soldering iron, you won't discharge into it. So what I've seen with many scientists, professors down to scientists, they have a tendency to practice ESD at the workstation. They'll put it in a shielding bag, then they go back to their desk to put it on a microscope, and there's no protection mechanisms, okay? Working off a desk. You can't do that, especially when there's portable field service kits, or you can have a portable mat using a wrist strap. That'll save the day. And once you work on it, you place it back in the shielding bag, and then you put it back in operation. So, with the big satellites, you usually see them covered with these metallized shrouds. Well, what's really great about CubeSats, the shrouds can be a Type 1 U.S. Navy approved moisture barrier bag, okay? That offers RFI EMI shielding. And here's what I've done. The pod, the CubeSats are enveloped in the Type 1 bag that is qualified by a guy named Frank Magnifico of the U.S. Navy. And if it passes that testing, then it can be suitable for a shroud for CubeSats at low cost. So to test it, we use this test method here. We use a simulator. We discharge 1,000 volts into the bag, and there's a capacitive sensor there, and this is what we're trying to meet, MIL PRF 81705F, which is the test method STM 11.31. So 1 kV is equivalent to 50,000 nanojoules, roughly. We don't want to see, according to the DOD, more than 10 nanojoules. However, this Type 1 bag is a true Faraday cage in that it only allowed, on average, 0.11 nanojoules. That's really good. Okay, that's getting with the program. So we can honestly, once we package the CubeSat in this and we seal the bag, we can walk from area to area, even outside the ESD protected area, and be assured that we won't see EMI RFI emissions. So, a Kentucky windage method, shade tree method to verify that is to set your transistor radio on the AM band, and let me see if I can get this, hopefully get this going. Yeah, here. As we place it inside, it should silence that. Shows you right away it works. So I know that's $10 from the old Radio Shack. Instead of buying that $28,000 capacitive probe test thing that I have, but it gives you a good high confidence. You would not use a Type 3 static shielding bag because it'll protect against electrostatic fields. But if someone has a cell phone and there's a low signal, then it'll boost the signal and it can penetrate the structure of a shielding bag. So you want a Type 1 aluminum bag. Okay, means all happy here. And we're happy because, let me see if I can go back here. See if I can get this. You guys, can you get this? Yeah, there, I'll let them do this. Three, two, one. It deployed successfully, and that's what we're looking for. Now, to generate a signal, I'm going to let them get this going. Airborne, airborne leads the way. So it did what it's supposed to do. Now, that's because product qualification equals successful deployment. And now we're looking at architectures that utilize various materials that will provide shielding and ESD protection. You want to do two things. You want to shield from discharge electrostatic fields, EMI emissions, and also when it deploys, you have friction or tribal electrification. And when it deploys, you don't want it to create a field enough at a speed where it creates what they call a field-induced model discharge. So, in salute to the Naval Academy and the Coast Guard Academy, Air Force Academy, that's me when I was 19. So, go Army. Who has the first question? Thank you. Anybody have a question? Yes. Yeah, I was at another conference. It was a NASA AAQ on CubeSats. And yes, in that they couldn't identify it at the time. And I had to deal, and I was the first guy out there talking about this. And, you know, most of them were from the academic community. And it finally clicked that, yeah, this may be happening. And one of the professors got up and said, you know, folks, for us to get the big money, this $80,000 has to work. So Auburn University has implemented a full ESD program. I can see Cal Poly is taking precautions here too. And I'm sure the Naval Academy is adhering to that. And does that answer your question? Yeah, there's been some stuff in the space station where they've had some problems. And what we're dealing with is, unless it's a humidity-independent material, that means it doesn't rely on moisture for performance like a topical surfactant or anti-stat. When we get below 9% relative humidity, according to Dr. Ray Goff, Kennedy Space Center, retired, and also Dr. John Collier of the Boeing Company, who's no longer with us, they discovered that below 9%, a lot of these ESD topically coated products would not work. So we have to go to inherently conductive polymers or carbon nanotube type technology for it to not charge and separate. I've done work in aircraft where we've seen issues too from shock and vibration, and you can map that. So we can bring the humidity down here to the shock and vibe to represent, you know, when you're launching, there's tens of thousands of miniature ESD events, but we want to make sure we can get rid of that from the onslaught. Some of the circuit cards from space and defense cost upwards 800 grand, you know, where if Apple's making a bunch of iPhones, you know, their circuit cards may be a couple dollars a piece because they can amortize the setup and over the volume. So you as researchers and such, you need to take the extra step. And besides, you can prototype now and do a lot of things on your own. So you don't have to commit yourself to big tooling that your predecessors had to be concerned about in the past. Good question. Anybody else have any questions? Yes, sir. Yes, big thing. In fact, at NASA, I've certified markets this area, and another area you saw a presentation on a rotisserie type thing, and I conducted EMI evaluation. And even on Earth, you want to make sure you don't kill it here before it deploys, but humidity is not your friend. Santa Ana winds, case in point. NASA Armstrong. It could be 50% relative humidity. Santa Ana winds kick in, the air is so dry, you're at 4%, sometimes 7%. ESD events just escalate. Did work for a company where winter conditions, they made circuit cards, and you could see through the winter months of December, January, February, March, they had exponential growth in their damage with circuit card assembly. And this is 10, 15 years ago. It's worse now. Good question. Thank you. Anybody else? Well, thank you very much. Yes. I got one more question. What you notice when I did the decay test, the spring load, and I wanted the electrical conductivity. At first, it wasn't providing that all the way through. And that way, you can have an isolated conductor that could be charged. But if you're neutral and everything has continuity, when it deploys, you should be good to go. Thank you.
Thank you. Okay, now we have our scheduled break. We come back from our scheduled break. Session 6 starts at 3:30.
Welcome back from the break, and I would like to present our next speaker, Jan Stupel from NASA Ames, presenting the Pi-4 mission, a low-cost demonstration of multi-CubeSat coordination.
Right. Thank you very much for the intro. And thank you very much for all of you coming back after the break. Nice to see some faces in the audience. So yes, I will give an overview of the Pi-4 mission. And so this is a 4 CubeSat mission, 1.5U CubeSats. And we are demonstrating a range of different technologies that are relevant for CubeSat swarms. Let's look who is involved. So Carnegie Mellon University is in charge. The PI is Professor Zach Manchester. We have support from NASA Ames, namely Max Holliday, who is providing system engineering support, INT support, electrical engineering support, and mission ops support. And my name is Jan Stupel. I'm the project engineer, and my role is mostly the interface between the mission and the sponsor. The sponsor is a small spacecraft technology program. That's a NASA program based out of STMD, and the program office conveniently is located at NASA Ames, which makes it very good for me because I don't have to commute back and forth. The main focus of the mission is RF ranging, and let's look quickly at the content. So I will start with the mission overview, obviously. I'll talk about how the mission was implemented, and we actually launched already March 4th on Transporter 10, so we have initial on-orbit results. Nothing is final, but enough to give you an idea what happened so far. So let's do the mission overview. So, as I said, Pi-4 aims to demonstrate a whole range of different things relevant to CubeSat swarms. And the most important thing about swarms, in my opinion, is that they are able to take coordinated multi-point measurements. For example, be in the solar wind and take dispersed measurements in different locations at the same time. Ideally, they do that somewhat autonomous and cost-effective. And the most important thing here is, in order to take those multi-point measurements, they need to know where they are in respect to each other, and ideally also in a absolute fashion, because if you don't know where you are, the measurement is not really valid. The one part here also is that on Earth, obviously, we can rely on GPS, but NASA is also interested in different locations of the solar system, so we try to do something, obviously, not depending on GPS. And so the idea is to use S-band ranging between the spacecraft to figure out where these spacecraft are in relation to each other. We want to do coordinated radiation measurements, just to have an example that this actually works in a real-world case. So this is not a science mission, but we are using these radiation measurements to demonstrate that things are actually working as expected. So our ranging can go into the position determinations. We also want to do over-the-air software updates and mesh forwarding of these updates. And another interesting point is to do 3-axis magnetoker-only sun pointing. So go for a way where, for an approach where you don't need reaction wheels and still get some half-decent pointing. And if that works, you can also do differential drag. So the things that I mentioned have quite a few overlaps, which technology development that NASA is interested in. This is a whole big eye chart, and I'm not going to go into the detail. The bottom line here is just that this touches a lot of relevant technology disciplines. And that brings me to the implementation. Wondering, I thought I had a clock somewhere, but let's start how Pi-4 is built up. So as I said, we are talking 4 spacecraft. This is a view into one of them. You have in a 1.5U chassis, and the whole system is operated by the Pi-Qt motherboard. What does that mean? So the processor is, the flight system is programmed using Python. So that's, by the way, is why this whole thing is called Pi-4. And the system is called Pi-Cube. That is open source, developed by Max Holliday and also maintained. And I believe a couple of universities who presented yesterday are using this system as well. This is a version 5 iteration of that mainboard. And this is basically driving a bunch of radios to do the RF ranging and other things. So I'll talk about the radio subsystem later. But let's talk about the other components. So you see there are 12 batteries in there, 16550 lithium-ion batteries. We have solar panels that do unfold. So we have this on this side. You have the same on the other side, which is not on this picture, but symmetric on both sides. And hidden in those panels are 2 things. On the one hand, there is a PCB loop in here, multiple loops, and these are actually the coils for the magnetorquer operations. And also in here is an S-band dipole antenna. What you also see is the additional antennas. Obviously, you have the classic tape measure antennas for the UHF part. You have a GPS patch antenna on here. And you have all sort of other interesting things hidden, like there's an IMU in here, and but this is the high-level overview. I promised a little bit more details on the communication subsystem. So on the right, you see what's happening on the Pi-Cube mainboard, and this is a S-band LoRa transceiver and a UHF LoRa transceiver, and the S-band is mostly used for the ranging operations, and the UHF is our main communication link to the ground. And there are 2 things that are happening. On the one hand, we have 2 dedicated ground stations, both at NASA Ames and at Carnegie Mellon University, also for commanding, obviously. But the advantage about LoRa is that there is a whole network of amateur ground stations around the world, and those are picking up radio beacons. And that is instrumental for the success of the mission as well. Other communication-related payloads or subsystems, we have a radium transceiver as a backup communication link. We have a Novatel GPS receiver to verify our ranging measurements. And finally, what you see on your left, there is another Raspberry Pi in there and an SDR, and this is basically an additional payload stack that the PI and his grad students can program independently of the main spacecraft GNC. It has the advantage if something goes wrong at this point, it's not impacting the rest of the spacecraft. So, and there are some ideas about future experiments after we're done with the main things, like using the SDR there to do a GPS receive and other S-band, and other interesting S-band experiments. So I'll talk a little bit about the algorithms here. The ranging is a time-of-flight ranging. So one of the spacecraft takes the role of the chief. So the spacecraft all 4 are identical, but it's just a software switch, so to speak, that turns one into a chief, sends out a ranging request to one of the followers. It's processed over there. They send a package back, and the chief measures the time of flight, and there you have the range. And this is, as I said, utilizing LoRa. That's a long-range communication modulation. It's a spread spectrum chirp, and Max assured me that is basically the one very convenient and very accurate way of doing these ranging packages. And yeah, that's what I wanted to say about that. Let's look at the magnetorquer demo. The sort of secret sauce here to get high accuracy that you would expect from a simply detimable operation is that the algorithm has a priori knowledge of the magnetic field and can basically adjust itself in a way so that to get higher accuracy pointing. So that's why the hope is that there is a decent 3-axis pointing only using these magnetic coils. And Zach Manchester has a paper out on that. If you're interested in all the gory details, happy to point you towards that. And then I want to quickly talk about how the radiation measurements are done. And these are done with a tiny RadFed chip here that is integrated into the spacecraft. And the idea is to take measurements coordinated of these 4 spacecraft in the South Atlantic anomaly at 4 points at the same time. The next step, what I have here is an overview about the INT. What you see on the top left, sorry, it's very small, but it's basically that's the part for one of the 4 CubeSats, multiply by 4, and you get the whole system. You see the solar cells, you see battery packs, whip antennas, and so on. And in regard to the INT flow, we started in July 2022, had the official kickoff in October 2022, and basically at this point we're already starting to build up an EDU, and we put that EDU to quite a rigorous testing regime. So there was a vibe test, there was a TVAC test, there was a lot of outdoor testing. So we are lucky in the Bay Area that we have quite a few mountains and hills around. So we did what's called a ridge test between 2 mountains, around 20 miles, to test the link budgets of the radios. And if you ask, oh, how do you do that? Did you get a license for that? Well, the good thing about LoRa is that it's in the ISM band, so you don't need a license. So we could be able to do these outdoor tests without a specific license for that. For the actual mission in space, you still need your NTIA license, unfortunately, or fortunately, depending on which direction you look at. So that took a long slot of time to get that done. But yeah, after the initial EDU testing, we went into build, and there was a vibe test, obviously, before delivery. And then that was last fall. After that, a lot of mission simulations, and then delivery in January to Maverick Space Systems, who was our launch integrator, and then the launch in March. So Pi 4 spacecraft launch March 4th, 2024. A lot of 4s here on Transporter 10 into the usual sun-synchronous orbit at 525 kilometers altitude. Inclination 97.5. As I said, launch service provider Maverick Space Systems of San Luis Obispo, who happen to have a booth up here. And let's see, if you look here, that's the dispenser on the upper stage, and there should be a satellite coming out, or 2 satellites coming out over there, if you squint. So there they go, and then the second deployment will happen around here. And yeah, that's all I want to say about the launch. So let's talk about initial results. So concept of operations after deployment, there's the usual wait time. So you have to make sure that you do not interfere with other payloads or the rocket here. So there's a wait time of 30 seconds that was mandated by SpaceX. After those system boots up, there's a couple of minute wait, and then there's a burn wire that deployed both VIP antennas and the solar panels. At that point, RF transmissions begin, and the mission actually goes directly, automatically in the normal operations and do the RF ranging. There's the option, or was the option, of going into a magnetorquer detumble at that stage, but we got lucky. We had very benign tumble rates when we came out of the dispenser, so we were able to skip that basically. And so this is a list of the Pi 4 level 1 tech demo threshold requirements, and I took the liberty and checkmarking all of them. This is not quite the entire truth, because we received all the data to do these tasks basically, but the data analysis, especially for the ranging part, is still in progress, and the whole mission is still in progress. So let's call them preliminary check marks so far. So again, first goal was the S-band high precision ranging. So the spacecraft exchanged a bunch of ranging packages right from the beginning, so that worked well. The actual mass to do the topology determination, that's still in progress. That's for this mission. This is ground-based. It's not on spacecraft. The spacecraft collected a lot of radiation measurements already. There were over-the-air software updates already. You know, this is a success, but it also means there will need to changes. That happens. And then we already implemented the 3-axis magnetorquer demo for the pointing. So this is a view on the left as a dashboard for the mission. So you can look at all 4 spacecraft and see what the status is. You can see as a snapshot the battery voltages are very much green, and it turns out they were very much green all the time because the EPS is kind of over-designed, and yeah, so batteries are basically always full. On the right, you see count of packages exchanged. So this is a snapshot in the beginning of the mission, and so as I said, there was lots of exchange of ranging packages. So this is going into the magnetorquer sun pointing. So you see 2 views basically of the unit sun vector. So all the black dots is one snapshot of the IMU basically, the sun vector, and when you see this turning green is when the magnetorquer is turned on. And when you see things getting into this blue circle means that the sun vector is aligned to a degree of at least 10 degrees. The solar cells are aligned with the sun vector at this point to 10 degrees. And at this point, the algorithm turns off, and at least for this part of the mission, that's counted as a success. We plan to run this longer and see whether we can get it better, but again, we just started March 4th, so that's what we got so far. So this is the top view, and this is a side view of the same thing. Then the next slide shows the Pi 4, how it demonstrated also with magnetorquers, but this time the pointing is not towards the sun, but it's a demo of a spin stabilization. And you can see this is X, Y, and Z axis. And you see that it starts, somewhat random tumbling here, low tumble rates, but at this point the coils are turned on, and you see that X and Y stabilize around 0, and the Z axis is spinning up to about 20 degrees as planned. And as I said, that's all happening just with the magnetorquers. You can see it takes some time, so it's about 20 minutes to get there. The other plot I showed you before, that was 40 minutes to get there. Reaction wheels obviously will be much faster than that, but you have to have reaction wheels. So at this point, I want to look at a few conclusions. So primary focus here is onboard autonomous navigation and control algorithms to test them out in orbit, and that obviously started to work already pretty nicely. This is built on a mission called VREX that has an orbital and suborbital part, and checking a few more boxes that VREX couldn't do. The range-based navigation techniques provide a low cost and low swap alternative to optical relative navigation systems, obviously, because you don't need a camera, and all spacecraft have radios on board anyway. He provided a demonstration of magnetorquer-only pointing. That could be a fallback to recover spacecraft that have failed reaction wheels, or obviously support spacecrafts that don't plan to fly reaction wheels at all. We demonstrated the over-the-air software updates. This can extend lifetime of satellites. Both, gives you ways to change mission goals late in the game if you're still out there, or you can correct for errors, obviously. And last but not least, Pi 4 continues, and the Pi-cubed open source avionics stack, developer Max Holliday. So this, as I said, is open source. Many universities have used it before. So this is, another step on this path, so to speak. Okay, I have then just please let me get to this, my thank you slide. You see the team at NASA Ames, at CMU, support from Ames TVAC, Ames Spectrum Management, Iridium Maverick Space Systems, SpaceX, and last but not least, our sponsors, the Small Spacecraft Technology Program. Thank you. Completely ignored, so do we have time for one question, or are we completely out?
I'm afraid so.
Sorry.
Thank you again for your presentation. Now, please welcome Royce James of the U.S. Coast Guard Academy. He will be presenting Sea Lion through U impedance probe space plasma measurement investigations.
It's really nice when you can bring your own posse with you, especially when it's a borrowed posse. Thanks, Navy midshipmen, for that wonderful applause, and the rest of you as well for sticking around. My name is Captain Royce James. I am a physics professor at the Coast Guard Academy. I am a fusion scientist. I actually work on tokamaks and stellarators. But on my side hustle, I look at and build CubeSats with my mechanical engineering friends. I wanted to first also offer an apology. I've been under the weather all day today, as you saw with the mask coming in. So colleagues, I missed most of your talks. I will watch them, but I just wanted to let you know, in case you haven't seen me, that's why. So let's talk a little bit about the Coast Guard Academy. We have a collaboration for space and energy. One thing that you'll learn about the Coast Guard is that we're small. We're about the size of the New York City Police Department, and we go worldwide service. We have folks and assets, including ships in Bahrain, in the Persian Gulf, in Japan, all across the world. And so we have learned really quickly to do more with less. It's not a mantra you want to hold on to, but it's what we have. So in our Collaborative for Space and Energy, which is kind of a nexus around the Helicon plasma experiment and the plasma lab, we look at things like water treatment, from plasma water treatment. We also look at, of course, our space work, which is what I'm going to talk to you about today. But the jewel of the fleet for the energy side is the Helicon plasma experiment, where we build diagnostics for fusion research. So nothing happens without collaboration. I'm sure all of you know this, but we're just pointing it out here, right? That is a long list with a lot of logos, right? I'm not even gonna read them all, but they all have a piece in having us here and getting our spacecraft launched this September. We also have an academic inside of the gates, as we say at the Coast Guard Academy, and then outside of the gates, with our main partners, Old Dominion University on this spacecraft, Sea Lion, and then of course our professional Coast Guard and outside businesses and organizations. So we put together this group called the Military Service Institutions of Higher Learning, MSIL, right? It hasn't quite stuck, but I'm still working on it. It's really a way for us to get all of these folks together. And hopefully you're recognizing West Point and Naval Academy, Coast Guard Academy, Air Force Academy, all these folks. Actually, West Point wasn't here this year, but all these folks you've probably seen before. But maybe you didn't notice the Naval Postgraduate School and AFIT. Those are the graduate schools for the military. There's two. One is in Dayton, Ohio, right? Not very glamorous, but around lots of stuff, right? That you can do science and STEM, and that's the Air Force Institute of Technology. And, oops, sorry. And then there's the Naval Postgraduate School in Monterey, California. Much better gig. Midshipmen, if you can get to Monterey, go. It's beautiful there. Please, and say hi to Gio when you go. So we put together this group to equip, staff, and discover. I would love to read all these things to you, but that monitor is way too far from me, and me turning around and reading the slide is not a good idea. But I do want to point out a couple points when this equip, right? We want to bring folks together. There's never enough equipment, right? We borrowed an S-band antenna just a year ago from Navy, right? They borrowed some stuff from us. We shipped them things from AFIT, right? Like, we can't do these things on our own because our programs are not big enough. Specifically, the Coast Guard Academy is about 1/4 the size of the Naval Academy, Air Force Academy, and West Point, right? We have about 1,000 cadets, and they have about 4,000 cadets. So you can get a sense of the scale, right? So working together really helps all of us. And then staff. There's some really great lessons that you learn in bureaucracy, as I'm sure you all know, but also the science, and especially when you're talking about military science, that we can all share together. Right, so Captain Sanders and I can sit down on a phone call and we can trade stories with, with Jen, one of our professors at the Naval Academy, and with Lorraine, one of our professors, make this thing happen, and that's where the magic happens, the magic sauce. So, and then discover, and I am gonna read this. We wanna prepare our future officers, technicians, civil servants to carry the torch of discovery to meet our future missions, right? That's what this group is all about. It's about getting into space, but it's also making sure that we have a way to move forward as we grow our new coming shipmen, midshipmen, cadets, the whole lot. So I'm going to talk to you later about Mission Sea Lion. If you were here for Richard Freeman's talk yesterday, which he smashed that out of the park, it was such a great talk, right? We're going to talk more about that today and just give the other side of our payloads. So if you were there, you learned about our primary mission, right? We really need to test our MC3 network, which is a collaboration with the service academies and some other colleges and universities. But we also want to validate our DECS experiment, affectionately known as the DECO. Don't ask me why it's an O instead of an S. And then our tertiary, which has become more of our primary, is that whole thing you heard yesterday from Richard Freeman about using Doppler shifts to locate mariners in distress, and also eventually to use it for communications in the Arctic, right? A huge piece of what we're doing. So let's talk a little bit about the impedance probe, which is one of the main payloads on our spacecraft. The impedance probe is made of a wonderful, and this is, excuse me, I'm getting used to this, sorry. This is a wonderful old, that's the old impedance probe. Our new one, we don't have a picture yet because it comes in next week, but we should have a great picture of it soon. This impedance probe board allows us to measure temperature and density of plasmas in and around the spacecraft. So we can see how our plasmas are charging up the spacecraft. We can see if we're getting lots of density and wherever that spacecraft is flying. The wonderful thing about the impedance probe is this side strap antenna. I'm gonna get this. This side strap antenna, of which there's two. It actually isn't here. It's actually gonna be here and here. This is an older picture, but it really illustrates how thin and small that antenna is. With that antenna, we can take measurements, again, of temperature and density wherever the spacecraft is going. We can also trim, we can also trim this antenna and use it on smaller spacecraft. We actually built a ThickSat, which was like 2 CD cases, where we did that very thing. Right? We tested it in the chamber, and unfortunately, when we launched it, was it NG-18, I believe, where we had a catastrophic failure in the launch Everybody did. Nobody's satellites made it out of that tube. So we haven't tested it in space, but we have tested it inside of the chamber. The DECS system, right? This is the deployable composite structure. This is a carbon fiber filament that spins out of the spool only from the tensile strength of the actual carbon fiber, right? So there's no springs, there's no mechanisms, there's no motors. It's just a carbon fiber that's been 3D printed. Not really, it's been extruded. And then we roll it up, and this is ODU's payload. They roll it up and then expand it. I thought this was a really great thing to talk about, and I didn't realize the talks that were happening yesterday. However, we had talks yesterday that talked about drag sails and drag sensors, right? We are always talking about adding extra UHF and VHF dipole antennas, right? The magnetometer boom, right? Micro debris sensors. This composite material can be used for that very thing. So that's what it looks like in reality. It's about 1 meter out from each side. It's very large, right? This also can use attitude control because it's going to change your angular momentum. It can also, of course, slow down and brake if needed, depending on how big you make your carbon fiber. So, and of course, the last payload is the Doppler shift that we talked about. I'm not going to spend much time on it because, like I said, Richard did a wonderful job. But if you missed it, definitely find us. You're going to want to talk to us about how we use this elevated Doppler shifted signal from a spacecraft to then localize from where that spacecraft is, where a mariner or someone that's in distress is in the Arctic or anywhere else really. But really, it's for the Arctic where we have a lot less communication capabilities. Okay, so here's an animation of our orbit, and as the world turns, you will eventually see the Coast Guard Academy, because a lot of people ask us, where is the Coast Guard Academy? It's a fair statement, right? Fair question. Here it is. There it goes. It's in New London, Connecticut, exactly halfway between New York and Boston on the 95 corridor. And on our Smith Hall, the science building, we have a ground node for the MC3 network. We also have a ground node that we're responsible for in Anchorage, Alaska, that the Coast Guard operates on our own. Okay, so Richard already told you why we need the Arctic and why it's so important for our Doppler shift experiments. I'm going to tell you that from a space weather standpoint, most of the interesting things that happen are in this very same area for a polar orbit. One really nice thing that we don't have time to have a video in here, we don't have time to show it. We can look at the effects of magnetic reconnection, and we can see from those reconnection points how much we have an influx of both temperature and density in the plasmas that are interacting with the magnetopause from the solar wind. Because of our orbit, we're going to be right in the soup, right? So this is a great place to have our impedance probe to be able to measure those changes as the solar days go forward. So we did some measurements of the impedance probe, and it is impedance, right? When we're looking at regular old general Ohm's law, right? V is equal to IR. This is not that, right? Because we have an alternating current, right? An AC signal that's coming from a DDS that's creating an impedance. And at some point, you get an impedance match. From one antenna, we send a signal through the plasma. And because when the plasma is ionized, it makes the electron move back and forth and oscillate. That plasma oscillation becomes a plasma frequency depending on the temperature of the plasma. So if I have a high temperature plasma, I'm going to have a high plasma frequency. If I have a low temperature plasma, I'm going to have a low plasma frequency. As I'm moving my actual DDS through the multiple frequencies, I'm eventually going to get a match. And when I get a match in this circuit, that really nasty eigenvalue becomes something that's really easy, just V is equal to IR again, right? There's V, there's I, there's R. And so when that happens, we get a phase flip, and that's how we know we've actually hit the magic number. So we tested this at Naval Research Lab in their big chamber. Now we're doing some preliminary tests, or some follow-up tests in the plasma chamber at the Coast Guard Academy. That's HPX. And just to show, that's HPX when she's on. Right, and so we can vary the temperature and density of HPX. I won't get a chance to talk about all the ways like our Thomson scattering device, our optical emission spectroscopy that we can measure the actual temperature and density of those plasmas to compare, but we do have those. Okay, so once we find the plasma frequency, we can literally just compare it. We don't need to go through a full circuit. This is for circular, this is for our actual linear surface-mounted probe. Whatever we dial up where we have this phase flip, that is the actual plasma frequency. And then we can take that and see how it changes. Those phase flips change as we move through different densities. So on the left here, this process of impedance probe was used on ISS in the SPADE mission. And for a good 5 years, this is how ISS knew if the spacecraft was being charged. And the difference between the SPADE mission and our mission is that we have these dual strap antennas. SPADE has a really large, almost meter in diameter sphere that they put on ISS in order to make this calculation. So we wanted to show that the data that we were getting in space at ISS tracked with what we got at AFRL in our first experiments. Those were successful. We then wanted to see how our measured densities matched at AFRL. And so this is, again, the densities that we were getting from the phase flip, and this is us doing the calculation to find out what the actual densities are. Turns out that we're tracking nicely with what's happening in SPADE, or what happened in SPADE in space, and what's happening now when we take our measurements. So lastly, this wouldn't be as good if we weren't able to measure temperature. So we are able to actually measure temperature in a very typical Langmuir probe method, where we bias our actual side strap antenna, and we're able to take advantage of the IV curve, like you normally would for any other impedance probe, and utilize that same method. The difference is I can put this on a CD case and get temperature and density, but a Langmuir probe, I can't. There's no batteries that are going to be big enough, or the batteries are too big. Okay, so we did have one problem with capacitive loading, and here's our dual strap antenna here inside of the NRL chamber, and we weren't not getting the right capacitance that we expected in order to make our calculations. So we did some troubleshooting, and it turns out that once we actually put a little more dielectric in between the chassis and the antenna, we were able to get the capacitance that we needed. This is actually something that is troubling me, because when you're on ISS, you have the entire spacecraft to get the ground, right? It's a pretty large ground. They plug their laptops in it, they run experiments. It's a large ground, right, to take a reference for the Langmuir probe, right, to actually find your temperature. For us, it's just going to be the spacecraft. And so if we get capacitive loading in here, that's going to affect how much we get access to ground. It's going to change our float, right? And so the only float that we really have is the float of the batteries, which hopefully will be enough. We'll see when we stick it in the chamber in another couple weeks. All right, with that, I'll ask if there's any questions. Oh, please. So I haven't collaborated with Dartmouth on this program, but we do have some other collaborations. I'll put some feelers out to see where we're overlapping. Thanks for that. Any other questions? You're all ready to go build your own impedance probes on all your devices. I'm so glad to hear it, right? I will put it out on open source, just slap it on, put it in, please, by all means. So I wish I could give you a lot more information on that, but that's Old Dominion University's payload. I know they use carbon fiber for a couple reasons. They wanted to have something that was going to maintain its tensile strength. They wanted to be able to do a lot of the things that we said, right? To be able to interact with electromagnetically with what's in the surrounding, and they wanted to be able to use it as an antenna potentially. So by making it electromagnetic carbon fiber makes it so you can actually be able to do that. It's a great question. Oh, please.
Another one on carbon fiber for you.
Okay.
Do you know the duration where you can keep that stowed in orbit and still have it deploy successfully?
So we talk about that a lot in our weekly meetings. And so for the tests that they've seen now, they've kept it over months and it's still deployed. And so the only thing that we're planning to have that when it's in the ejection tube is a spacer, and it's going to be on the door. And so it's the first thing out of the deployed tube. We have actually a bunch of solar panels. I don't know if you could see, it was really weird looking spacecraft because we started off with only a 4 to 7 day mission, and then we became a potentially up to 3 to 4 year mission. So we added solar panels, and then we added solar panels with all of our antennas. We had to put them in weird, configurations. So between our UHF antenna and our solar panels, we are going to have a burn wire that holds them into the holds it down before it goes through the tube, but the deployer for the deco is going to be just friction. And so far, so good. It hasn't given any trouble. Of course. All right, 2 minutes for another question if there is one. If not, I will yield your time. Thank you so much for your attention. Oh, please, Richard, of course. Sure. So a Langmuir probe is when you bias a tip. There's many different kinds of Langmuir probes. There's mock probes where you can take 2 tips of a wire. Just imagine you have a wire, take 2 tips, you put a battery on it, bias one side positive, one side negative, stick it in a plasma, and you can measure the flow by which, it's hard when I only have one hand, by which way the plasma interacts with the first tip and then the second tip, and that's called a mock probe because you're looking at velocity. You can take 3 tips and have a floating, a negative, and a positive and make a triple probe, which instantaneously gives you temperature and density without doing any extra calculations, right? You can have a traditional mock probe where you pretty much 2 tips again, turn sideways, and just looking at how much current is flowing through those probes. When you look at the current flow, when you look at that current flow, it follows this IV curve. From this IV curve and the actual geometry of your tips, you can literally back out the density and the temperature of your plasma depending on what your bias is and how much current you have, right? And so these are used all over the world in all different kinds of experiments, from fusion experiments to plasma processing to water treatment to space. And our ansatz is that in order to do that in the spacecraft, you have to have a fairly large battery and potentially have some power issues by how much power you're using. The DDS of the system offers the bias here and does the frequency change, which is really small. We're talking like ½ a watt, right? So we're talking really small amount of energy that's used in the impedance probe, hopefully to get you the same thing. So so far, it's done that in ISS on Spade, much bigger antenna, but now we're going to try it on our side strap antenna. And I'm getting the stop sign. I don't want a cane. So I'm going to say thank you for your time and attention and the wonderful questions.
Hi, everyone. Yes, I think you can hear me. That's wonderful. So, yeah, I'm going to be presenting a solution that actually one of Mike Galvin's students from Princeton University came up with, Anthony Matimu, and so came up with this idea and felt that it was a really good idea to use X chips for this project. So what we're doing is we are partnering with NanoRacks and Princeton University to actually launch one of these, send one of these nano labs to the International Space Station. So this is the model that Anthony's been using to test and build for his prototype. So this is a 1.5U, but what we're going to be doing is we're actually going to be flying a 2U nano lab. And what it is that each institution, school, middle school, high school, they have their own payload. And what we do is we make sure that they have power and communication. So they don't have to worry about anything else. It's all about what is the experiment that they're going to do on the station. So what it is that each institution gets their payload area, and it's very similar. On the screen right now, I have a photograph of a very similar rideshare unit that we are launching with the NASA Goddard office, with their balloon office, from New Mexico in August this year, 12th of August. And so you can see that each institution, they have one of the slots, one of the layers. And so they run their experiments and they save the data to the SD card on their layer. And what we do is we provide the power and the controls. So with those payloads that fly in that 1U on the NASA high altitude balloon mission, that is almost like a stepping stone to before going to the International Space Station. So why are we doing this? We're doing this because what we want to do is we want to give as many institutions as possible their first space mission. And what we're doing is we are giving them access to microgravity for the first time. So with this rideshare option, what it is that we integrate all of the payloads into our structure and into the nano lab. This nano lab then goes with one of the resupply missions to the International Space Station, stays there for, let's say, a month, maybe 6 weeks, and then it comes back with one of the Dragon modules, and then everybody receives their payload back. So it's not going to be deployed from the ISS, it's going to be there. There's these connection ports. So what it does is it actually clicks in and it connects to the NanoRacks infrastructure on the International Space Station. And so what we want to do is we want to make sure that student groups can have their first experiment, and they don't have to worry about communication. They don't have to worry about power budget, anything like that. That's all sorted for them. What they can do is they can focus on the science. And the International Space Station gives us microgravity, and that's something we certainly can't get on planets. So the payload layers now starting to get a little bit technical, and I know now in the next few slides I'm breaking one of my own rules, because what I do is I always say to people, you never put more on a slide than you would print on a t-shirt. So I apologize for this, but I thought it was quite important that I actually just take you through this. It's also going to help me when I need to answer the questions later. So what we have is each board, you can see here, where is the pointer is over there. Okay, so what we have is we have our, what we refer to as our extended core, which has the core processor here. We're using an ESP32. And then this is a prototype board which connects to a 20-pin connector we have over there. And what it is that the groups choose 4 X chips that they want to have as part of their experiment. So I'm not sure how many of you came across the X-in-a-box chips that we had in previous years. These X chips are an updated version of those X-in-a-box chips. And so what we also have is we also have the prototype boards. So if there isn't a sensor that we manufacture in bulk that the students would want to have, then what they can do is that they can actually use those prototype breakout boards, and then what they can do is that they can add their own SparkFun or Adafruit components to it. So as an example, this is a barometer. So this is giving us atmospheric pressure and temperature. And then this one with a little rocket on it, this is an accelerometer, X, Y, and Z. So yeah, typically 4 X chips. With the high altitude balloon mission, we have have as tight constraints, so they can actually have 6 X chips on that. So they reduce it from 6 to 4 for this ISS mission. And yeah, so what we're doing is that we really need to comply with the standard. As Geordie said yesterday, you know, you have to work inside the box. So this is the box that NanoRax has given us, so we are making sure that we work inside the box. And just to go into a little bit more detail, with the extended core, we have the ESP32. We also do have a serial camera control bus, which we're not going to be using in this particular mission on the ISS, because it's going to be inside the box, so we're not going to have the requirement for the camera. However, it's very useful on the high altitude balloon mission, which is the precursor to this one. So one can have the camera control, the camera, the SD card, of course, as well, and we have the extension slot, so that what we can do is we can actually communicate with what we refer to as these spines, where all of our communication happens, and then this has been joined to the base, but actually the board on the bottom here is our control board, and CAN bus transceiver. So if we take a closer look, what you can see is that there's 2 types of prototype board that one can use. The one that actually would connect to the 20-pin connector, and then the other one that complies with our normal standard of using I2C and 3.3 volts. So for those of you who haven't seen the X chips before, it's very much like Lego for electronics. Everything is a standard size. Everything runs I2C and 3.3 volts. And we click it together using these 10-pin connectors. So you don't need to have a lab. You don't need to have a lot of equipment. It's originally designed actually for rural schools in Africa. This is a South African accent you're hearing right now, but we found that it's really it's popular around the world. So we do have a poster. Anthony put together a poster to show. So on the layer on the floor above the coffee area, the entrance, there is a poster exhibit if you haven't seen it, and we actually have everything there with his poster presentation. And what you could do as well is you could also add more memory if you wanted to, because we do have an SD card interface that will connect to the 20-pin connector. So when I refer to the 20-pin connector, I'm referring to this one over here. So what it could do is it could slot in there. When we have other applications, we use this 20-pin connector for the LoRa radio. So for example, what we have is a tiny GS ground station, and we use the 433 LoRa radio for that. So we use that pin to connect it over there. Oh, that's interesting. I turned it off. Okay. Pick a button. It's all working again. Sure, my heart dropped, I tell you. So yeah, so there's a selection of X chips. So we've got 18 different X chips that we manufacture en masse. What we do is essentially these X chips we use to run STEM programs in schools around the world. So when we manufacture in tens of thousands. So this project is an example of a space mission that we have, because the thing is we can't run a space STEM program in an authentic way unless we actually do something in space. So there is a selection of X chips that they could have a look at, or otherwise use the prototype boards and build their own. So the power and comms are provided for. So what it is that, as I mentioned before, these connectors on the base of the Nano Lab, that is connected to the International Space Station, to their power supply in the NanoRax rig. And so what it is we receive power from them, and then we have a very limited data downlink. So what we what we do is that from our control board that just controls the power to all of the payloads, what we do is we have a health check on a very regular basis, a number of times per day. But the thing is, what we've also done is each group then gets a small data budget. So if they actually want to have their own health check coming through, then they can certainly do that. And what's nice about that is that it starts introducing the concept of, with every mission that we have, every CubeSat mission we have a data budget. We have a power budget, we have a data budget. So we're starting to introduce those concepts. This kind of project is very deliberately meant as a stepping stone to having a final CubeSat in orbit. What we want to do is we want to have all these various stepping stones so that you can test one aspect of your CubeSat at a time, and this is meant for what do we need to test in microgravity. That's essentially what it's meant for. And so these are the mission parameters. Our first launch with NanoRacks is booked for around July, August next year. So all of our programs, whenever we run a program, it has to fit within an academic year. We don't want students to graduate and then move on and they haven't been able to complete their project. So what we're doing is we've put this project together so we can start at the beginning of the academic year in the fall, and then we can complete it. Everything gets shipped to NanoRacks before the final exams next year, and then it gets launched after the final exams. And our current occupation is 40%. We can accommodate, in the 2U, we can accommodate 16 payloads. And what we have is we have 6 of those booked. So so we're looking at roughly 40% is booked, and so we still have a number of places remaining. And another shout out to Mike Galvin from Princeton, and as well as his team and his students, and especially Anthony, for introducing us to the NanoLab, because we've been looking for a solution for so long, and this is such an ideal solution for us. And so when people ask me how much is it going to cost, it's just short of $10,000. That is for the full STEM program in a middle school or a high school, the high altitude balloon mission, as well as the trip to the ISS and the return of the kit. So the way we've put it together is that because all of our programs need to fit within an academic year, it can be quite daunting for a school that's going to be doing it for the first time, because they may feel, we're not going to be ready in a year, we don't know, how do you spell X-chip? We're not going to be able to do it. So the way we look at it is we say, let's look at 40% to sign up. Then you receive all of your STEM kits, you go through the STEM program, you do the high altitude balloon launch, you recover your payload from NASA Goddard Balloon Office, and you can analyze that data, and then if you feel you're ready, then we book you on the NanoLab, and then you pay another 40%. And then you only pay the final 20% when you've received your payload back from the ISS. I was really impressed with NanoRacks, because when they sent through the contract to me, that's how they had it, that the final 20% is only after they've returned it, which I actually find really comforting. So we've made sure that we've followed those same parameters. So to begin, it's actually $4,000. It's not $10,000 to begin. It's $10,000 once you've completed everything. So if you find for the first time it's going to take longer than an academic year, that's fine. Don't worry about it. That's really okay. And so this is the 1.5U NanoLab, and that was used for the development. And then upstairs we have the 2U, which is actually finally going to go into. And this is a photograph of Mike that I kept. because this is from November last year, and their first child arrived in December. So Mike, I'm keeping this for posterity, but I have to say, you're looking wonderful. You actually look younger now that you have a child. So maybe we need to swap this one out. So the QR code takes you to the project on our website. And thank you very much. And I was wondering if you have any questions for me. Yes, Mark.
So you could, if you have room on a larger CubeSat, you just have a small pancake and then connect it to 3.3 volts and iceberg C, and you've got another sub-experiment.
Yes, you're absolutely right. In this case here, what we've done is we've made sure that we leave space between each of the payloads, so that one can have some circulation, etc. But certainly what we could do is we do have stacking connectors, so you could actually stack them a lot closer to one another. Yeah, they're not going to overheat or anything like that. Yeah, so they are small. This is how big they are. They're actually 32 by 32 millimeters. So 9 3 by 3 still fits within the CubeSat format. The reason why we can only do 4 here, ironically, is because the external dimensions of this nanolab have to be within the CubeSat format. So we're losing a few millimeters on every side. Yeah, thank you. Are there any other questions? Good. Thank you very much, and see you all later.
All right, thank you very much. Our next presenter is Dorianne Williams from the United States Naval Academy, presenting on integration and testing of a commercial ADCS for the Naval Academy Standard Bus.
Okay, good afternoon, everyone. My name is Midshipman First Class Jackie Gwynn, and we'll be talking about integrating a commercial ADCS system for our Naval Academy Standard Bus. So for anyone that missed the presentation yesterday, the Naval Academy Standard Bus is basically a modular satellite that will provide power, comms, and an onboard computer to be able to service any other payloads, whether that's from other universities or other commercial vendors. The mission statement of our team is basically to integrate Cube ADCS commercial products with the Naval Academy Standard Bus using our own homegrown hardware and software. And basically what we've been doing all year is integrating those two systems. Our team breakdown is shown on the screen. We have 6 people on our team. 2 of them couldn't be here today, but our overall breakdown consists of a team leader, and then we break it down into 5 subsystems. That's algorithms and simulations, electrical and C&DH, flight software, integration and testing, and structures.
All right, good afternoon, everyone. I'm First Class Nordgauer, and I'll be going over the concept of operations. All right, so first, we're obviously going to launch our vehicle up there, and then we'll deploy it, send a telemetry request to power it on, and then we'll go ahead and start that first detumble. So we're going to go ahead and reduce those angular rates, and we're going to get those low enough so that we can actually move on to our next phase, phase 3, and actually deploy the magnetometer. And one thing to note is this actually works in the undeployed mode. We deploy it to make it a little bit more sensitive, a little better, so we can get better readings, but it does function without being deployed. And then moving on from that, once we do that, we'll go into phase 4, Y momentum mode, where we'll do things like the Y wheel ramp up test and commission that first wheel. And then once we have successfully commissioned that first wheel, we'll move on into our last phase, which is 3-axis control, where we have all 3 wheels operating. And now I'm going to talk a little bit about the algorithms and simulations. So in order to simulate that kind of startup, that commissioning, we use some switching logic in our Simulink model and kind of broke it down to 4 different sections here, color-coded. That first section is the magnetic actuators there, so that detumble phase, and kind of used time steps to simulate the wait time between the telemetry requests. And then from there, obviously, we're moving on into that first wheel, that Y wheel activation. That's what you see there in the yellow. And lastly, we have our green, which is that 3-axis control with 3 wheels. And then you'll notice here there's another red phase. That's actually for testing because we did make our own. So all this is controlled by software that we purchased, controllers that we purchased. And then we did make our own in-house BDOT controller that we do want to test. And that will basically allow us to replicate it in the future in-house so that we have some space-proven software that we can hopefully not have to purchase in the future. We can just replicate what we already have documented that we made. And here's the simulation capabilities of that Simulink model. I would consider this moderately robust. It's not as robust as I would like it to be, but due to constraints of the computer that we had available, this took about 30 minutes to run. So like I said, if I had better computers, then I would like to make this a little bit more robust, but this does the job just fine. And I'll go ahead and show you here in a couple slides what those simulations actually did look like. But what are we simulating exactly? So what we're using this for is to kind of test our inertia tensors. Basically, we wanted to minimize those product of inertia terms. So we did that by adding dummy masses in various configurations. And as you can see here, case A was the no dummy mass case, which did work. It got through the whole commissioning cycle, but again, those product of inertia terms were relatively large compared to the principal terms. So we iterated this a couple times through B and C and D phase, and really just put the dummy masses in different locations to try to get those product of inertia terms down while completing the whole commissioning cycle. And we ended up at case D, that last case there. That was the best inertia tensor that we found, the best dummy mass configuration that kind of was able to operate the whole commissioning loop and get us into a state that we wanted to be in. And so right here is just one of those simulation results. So on the left side, you have the wheel speeds, and on the right side, you have the body rates. And as you can see, it can get all the way to 3-axis control with this. That little spike there on the left is the Y wheel ramp up test. And then on the right, as you can see, all the body rates go down to basically 0. And then once we finally do get into 3-axis control, they're basically 0 because, that's not spinning too fast there. Then moving on.
All right, good afternoon, everyone. My name is Braden Kaiser, and I'm going to go over the hardware that we're using. Most of this is from CubeSpace, but we do have some of our own parts that we made ourselves. All right, there we go. So on your guys' left, you can see our fully assembled ADCS that we have currently at the Naval Academy. On the right, you can see the exploded view of each stack of that ADCS. On the top is our sensor structural board. This is our the board we use for our sensor suite. Has the mountings for each of our 3 sensors that we have. In the middle, you can see our ADCS electrical interface board that we made. This contains the reaction wheels and the electrical connection to the Cube computer, which is shown in the bottom, and which I will talk about in the next slide. So the Cube computer is our processing board that we're using. It handles all of the telemetry logging and control, the estimator control algorithms, and then it manages communication between all of our ADCS components. And then some of its functions are listed at the bottom, mostly to help with any radiation effects while we're up in space. And then for our actuators, we have 3 small plus cube wheels. Most notably for the performance for this is the plus or minus 6,000 RPM. Gives a good amount of torque before they're saturated. And then our magnet torquers are the cube rods and cube coils. So for our 3 sensors that we have, On the left, it shows in our sensor suite. We have our CubeSense, which is both nadir and sun sensors, and then we have our star tracker, and then the deployable magnetometer. So for the CubeSense, this is configured either into a nadir or sun sensor, which is done by CubeSpace before we got them. For these, they have a field of view of 180 degrees. And then we also have 10 core sun sensors, which can be spread across the different faces of the satellite, depending on the solar panels, the other payloads that we are accommodating. And then we also have our deployable magnetometer, which Nor talked about earlier. This will be on the external of the chassis and will be deployed after or during the commissioning phase. And lastly, we have our star tracker, CubeStar. Most notably with this, with the star catalog that this has, we can get a fix a little over 99% of the time, as long as we are below our acquisition rate. Next, I'm going to be talking about the structures. So on the left, you can see the fully integrated ADCS with the standard bus on the bottom, and then our sensor suite at the top. The picture on the right shows that our sensor suite is flexible on its location a bit. With our structure board, it can move up or down depending on the payloads, the solar panel configurations needed, anything like that. All right, and then lastly, this is a picture just showing our sensor suite again. At the top, there is a typo. That is supposed to be the sun sensor, not the Earth Horizon one. It shows the configuration that we decided on. I wasn't involved in the trade study on what the actual decision to make this, but this was what they decided was the best way to get the performance out of each one.
Okay, I'm Midshipman First Class McCarthy. I'm going to talk about the electrical interface between our ADCS system and the Naval Academy Standard Bus. So the point of this is the Naval Academy Standard Bus has a 10-pin payload interface connection, and the ADCS module from CubeSpace uses a PC104 bus standard. So we need to somehow go from that to the PC104. And in order to do that, or because we need power and UART communications from the bus. So the best way we figured out how to do that was with a PCB, and this is kind of a block diagram of what that PCB looks like. It's just the 10-pin Molex. We only use 6 of the pins to the PC104 bus, and then we also use this as a structural mount for the 3 cube wheels. So turns out PCB design is kind of challenging. I didn't even know what PCB stood for before we started this project, so printed circuit board if anybody doesn't. But we use this open source software called KiCad, really awesome software, very user friendly. And once you learn how to use it, you can quickly design. Yeah, this guy uses KiCad too. But so yeah, next slide. We went through a few iterations here. On the left is our very first prototype. As you can see, it's a very simple PCB. The challenges came with all the nuances of KiCad and PCB design and all that. But so that was our first iteration. The second iteration, we thought we might need to regulate the 3.3 line on our end because of possible current limitations on the bus's 3.3 line. But later, we realized that was just unnecessary complexity. So the final board is there on the right. I want to talk about our prototyping methods. We had 2 methods. The first was a machine from a company called Volterra. It's the V1 PCB printer. It's just a CNC PCB printer, basically. It was kind of hard to learn how to use it at first. We didn't really have anybody to teach us how, so we just had to figure it out with a lot of YouTube videos. But once you get it, you can make a prototype in about 3 hours. And then our other method was just pretty standard, etching copper away from a copper-plated piece of plastic. And we didn't have the resources for this one in our department. We had to outsource it, and so it took a lot longer. And here's what the final board looked like. We used precision PCBs to professionally print it, and yeah, that's what it is.
So now I'll be talking about the flight software. So our job on the flight software team was basically to, again, integrate between the Naval Academy standard bus and the Cube ADCS commercial hardware that we were given. This integration, obviously, on the software side, we used UART to create those connections. And the standard format of communications between the Cube computer and the Naval Academy standard bus payload interface board was through two different types of messages, telecommands and telemetry requests. Telemetry requests would be sent in a specific format, which is dictated by Cube Computer's firmware reference manual. We would read through the whole thing and determine the specific format for a specific command. Send that request over, and the Cube computer would hopefully understand that in the way that we meant it to be understood, and send back an automatic telemetry reply with the data that we had requested. In a similar way, telecommands would be sent, again, in a very specific format dictated by the Cube computer and the firmware reference manual provided by Cube ADCS. We would send that telecommand over and would automatically receive a telecommand acknowledgement with basically the information, whether it was able to execute that command or a specific set of error flags depending on what went wrong if it wasn't able to execute that command. So our role on software implementation basically consisted of two key files, one being the library and the other being our main file, which is just called code.py. The library file basically contains a separate function for each command dictated by the firmware reference manual. We would read through the firmware reference manual and figure out the specific format for a given command, make that into a function, and that's what went into our library. So in the end, our library contained a ton of different commands and telemetry requests, as well as the software or the code to interpret the responses that we would receive from those telecommands and telemetry requests. The main file is actually the one executing those commands, and that's where we would execute the commissioning sequence, which again is provided by the Cube ADCS manuals. I think that's it. With that, I think we can take any questions.
Top right. No, that's on your guys' end. Your middle. So we have the core sun sensors, and then we have we have 10 of those, and then the actual sun sensor, and then yes, the star tracker. So we pretty much have determination covered with all of that. So yeah. Top left over here.
In your top section, you mentioned following your detumble and prior to establishing three-axis control, a test of the Y wheel. I was curious if you could elaborate a little bit more about what the intent of that test was.
Yeah, so that test, it commands the Y wheel speed to a speed that is a function inertia of the wheel itself and the inertia of the body, about the Y-axis, that is, the principal axis. And basically what we're wanting to see there is at that speed that we command, we should see 0 in the Y-axis. So we're kind of basically just doing that to ensure that we do have positive control of the satellite rates with the wheels before we go ahead and commission it and commission the rest of it.
What did you find beneficial in increasing the mass to get the higher principal inertias rather than trying to reduce the product of inertias?
Yeah, so our structures lead isn't here right now, so he would be the best point of contact for that. But based off me looking over his shoulder, what it seemed like we were trying to do is just add dummy, yeah, we could increase the mass. I think by adding dummy weights, we actually did kind of increase the mass a little bit. But the way we tried to do it was just by kind of reorienting that inertia tensor and not really like adding more mass to the principal axes, if that makes sense.
Okay, thank you for your time.
Our next and final presenter will be Graham Grable from Blue Canyon Technologies, presenting on increasing production efficiency through automation with evolving BTC x B1 CubeSat architectures.
Hey, good afternoon, everyone. I know I'm the last one, so I know you probably all want to get out, get some dinner, so I'll try to do some on-time delivery and make sure we get out of here. So thank you for coming to my talk today about increasing production efficiency with our XP1s. There's a whole group of people that helped me put together some information about this, including David Vickery, Shivani Patel, Devin Sanders, Zach Hurst, Matthew Barrett. So thank you to them for helping me put this together. And there's a whole team back in Colorado at Blue Canyon who really are the ones that are behind all the tech here. So for those who may not be familiar with Blue Canyon Technologies, I'll just give a bit of a primer for everyone. Blue Canyon Technologies is a vertically integrated company that has started its life really making components, reaction wheels, star trackers. We started to expand into full GNC subsystems like the Exact and FlexCore systems. We're really taking that heritage and that high performance of those components and putting them all into an easy-to-use, simple package. From there, we started repackaging these and putting more subsystems like power, radios, and creating our own spacecraft buses. And so today, we have spacecraft ranging from 3U CubeSats all the way up to Esper Grande Saturn-class microsats. As we vertically integrated, we've also expanded our product lines within each one of these realms. We've recently added CMGs, control moment gyroscopes, to our components groups. And last year, we've added the 16U CubeSat to our CubeSat portfolio. Over the past 7 years, we've seen a lot of growth here at BCT, whether it's across our components with star trackers and reaction wheels, or if it's within our subsystems like Exacts, FlexCores, and even within our spacecrafts. 45 of these alone have been XB1-based CubeSats. And these XB1s are the heart and soul of the BCT CubeSats, and that's really what I'm going to focus in on today. As we've grown vertically, and as you can see that we've grown in terms of volume that we've had to deliver, this has created some challenging choke points within our production workflow. To understand this a little bit better, let's take a quick look at our previous generation XP1s. These systems are tightly packaged, very dense. They pack a lot into essentially 1.5U of volume. We have our central processing unit, we have our radio, structure, SATA, reaction wheel, star tracker, all very tightly knit. This was designed with the right intentions, don't get me wrong, but this creates manufacturing problems. If we have to rework an electronics board with the XB1 integrated into a flight unit, this essentially required disassembling the entire spacecraft. That just really isn't the right thing to be doing. On the other hand, we want to make sure we credit the success of these XB1s for a few of the missions. These XB1s powered missions like Raven, Tropics, Tempest-D, just to name a few. To really focus in on the specific changes we wanted to make moving forward with these XB1s, let's take a look at Tropics in particular. As I mentioned before, the high density packaging of these XB1s created a challenging manufacturing challenge for us to overcome. To help mitigate this, we elected to build Tropics buses in pairs, both in terms of building the buses themselves and also in terms of testing. This allowed us to start creeping into automation and to help parallelize our production workflow. But going beyond 2 buses became unmanageable for both our test team, our assembly team, and our production team behind the scenes, helping to put together the parts. So this became a challenge that we wanted to address with our current generation of XB1s. The less tangible parts of these XB1s are the software. We have a couple different parts of the software that go into the XB1. There's the core underlying flight software. That's the stuff that talks to your payload and talks to our components. We also have onboard automation, so things like event checks that trigger off of telemetry off our bus and perform different actions that you define. Additionally, there are vehicle-specific configuration values, things like star tracker coefficients, magnetometer calibrations, spacecraft IDs, things along those lines. Those things are things that we expect to change on a per-vehicle basis, but we don't expect to be changing flight software on a per-vehicle basis. So we should only be changing the things we want to change, right? Well, with these XB1s, we were changing the flight software. We had to make a new flight software release every single time we made an update or changed one of those values we expected to update. This creates a lot of overhead for our flight software engineers, for our configuration management team, and ultimately on our test team, who are repeatedly having to rerun tests that were already verified. Now, in Tropics, we were starting to get into automation. Our test philosophy and our scripting philosophy is that about repeatability and consistency. What we want to have is really simple. We want to reduce human error, and we want to allow the test conductors to do more in less time. At the time of Tropics, about 20% of the test time was using automated test scripts. So a considerable amount of more could be done. So let's take a look now at our current generation of XB1s. From the ground up, we wanted to make sure that the design itself was modular in nature. It consists of an actuator assembly and a card cage assembly. The actuator assembly is similar to our exacts. It contains star tracker, reaction wheels, torque rods. Our card cage assembly contains the core of the avionics, power boards, controller boards, and configuration board. That's the main brains of our XB1. By making them modular in nature, we're able to parallelize the build of these XB1s and deconflict points where we're waiting on parts to catch up. This means that we can build, the actuator assembly and card cage in parallel, and we can have those waiting on the shelf, waiting for them to be put together to finish our XB1 assemblies. The build of these also allows us to remove card cages and parts within the card cage and parts of the actuator assembly while the spacecraft is still assembled. Thus, we don't have to disassemble the spacecraft to make a rework anymore. The way these modules and the XB1s are built allows us to also take advantage of the new internal manufacturing execution system we have. We switched to this new manufacturing execution system, and with the added parallelization that we have, we can now actually use some of the automations built into this. This means that now that we can push out work orders and assembly instructions automatically. This also allows us to have digital records of what has been done so far on an assembly, what hasn't been done so far on an assembly, and allows us to perform NCRs on specific steps so that we can further improve and quickly respond to problems and make sure that we flow that into our continuous improvement process and make sure we get it right on the next go-around. We also addressed our flight software, the intangibles. We now separate our base flight software from our vehicle configuration values tables. This is also inclusive of our onboard logic. This really helps us with constellation programs where we can now test flight software on a single spacecraft, roll that flight software to other vehicles, and do quick checks on those vehicles instead of a full functional suite, which usually can take half to a full day. We can now do that in a matter of minutes. Our process and methodology with testing still it continues to this day. We want to make sure we can do less, or we can do more, excuse me, with less time with our test conductors, and we want to remove human error and make sure tests are consistent. To date, about 60% of our tests are automated at this point. This allows us to jump beyond our limit that we have with Tropics with a test conductor running 2 spacecraft at a time. Right now, we can do about 4 to 5 spacecraft at a time, and more anecdotally, I've been told that we just need more computer I/O and really an iMac screen to do more. So we can really do a lot with the automation that we have in place now. Beyond our production line and into operations, we also have operational improvements with automation that we've seen. We have something in the pipeline called science data gap detection, where when a spacecraft is in a pass, we can downlink your payload data, and during that same pass, we can see where the science data gaps are in your payload, and we can make sure we get that data down in the same pass, so you don't have to waste another ground contact when you could be doing science data, getting that payload gap filled in. We also have onboard automation features like autonomous mission resume. This allows your vehicle to autonomously return back to nominal operations if, for example, a single event upset occurs. Our onboard logic sees that your spacecraft has unintentionally reset, pulls in critical data that the spacecraft has been storing the entire time on your orbit, returns your spacecraft automatically to your operations, turns on your payload, sends your spacecraft back to your science attitude, and resumes your normal downlinks. And finally, we've made some improvements to our bus commissioning, where now we're able to commission our buses very, very quickly. I don't know if we have publicly put out numbers, but we are on the order of an orbit or 2 of bus commissioning. So with that, thank you, and open for questions. I also have socks for anyone who has anything. Question back here? Great question. Here's a pair of socks for you. Yeah, so that's a great question. For those on the YouTube, the question was, how similar is our flight software between CubeSat and microsats and just across the company? It's actually very similar, and that's part of the intent here with being vertically integrated. The fact that we can use the same components across our product lines means that we really want to make sure we're consistent with our flight software builds. So things that we can do on our microsats can be translated over to our CubeSats and vice versa. Yep. Question in the back. Yeah, so again, I'm not sure if we've really put out too much numbers on like what our record so far has been, but in terms of what we do, it really comes down to the rigor and thoroughness that we perform in our AINT testing. You know, we go through the standard test like you fly routine. We make sure we have very realistic and representative day-in-the-life tests so that when we get to orbit, we're not finding a surprise immediately coming out of the canister. So that really allows us to make sure that when we hit orbit and hit the space environment, we're really error-free on that. So it allows our operations team to really quickly do checkouts and really send the spacecraft into the nominal operations very quickly. So here's a sock for that gentleman in the back. All right. If there's any additional questions, we'll be at our booth up at M8 tomorrow. Thank you, everyone.
Thank you very much. All right, that concludes day 2 of the workshop presentations. Thank you very much for attending. The presentations start again tomorrow at 8:50. Show up a few minutes early to grab a bite to eat before you enjoy tomorrow's program. Hope you all have a good evening.